Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another live stream. Right, hold on, let me share the live stream in my Discord server. Please join my Discord server so you can get notified of new streams, and you can also vote on next streams. So we would be happy to have you there. Right, let me see. One. Okay. Great. All right. Okay. Great. I have notified people now. All right. So to be clear, just a little disclaimer here is that I'm still a beginner at Async, at Tokio Async, and Async in general, and also multi-threading. And hello, Theo Paris. How is it going? How is it going? Welcome to the stream. So as I said, I'm still very much a beginner at Async and Tokio, and also multi-threading. And for Rust, I'm not gonna say that I'm advanced Rustation, you know. I could say maybe intermediate, something like that. But we'll see. We're just gonna go through it and see if we can figure out how to create a very high performance chat server that is both multi-threaded and also, of course, asynchronous. And what I mean by asynchronous and multi-thread is because they're pretty much different. So basically, your program can be single-threaded but still async, or it could be parallel but still not async. But it's different. So for async, you can have just one thread. So for every thread, you take full advantage of it. You don't just sleep the thread, and you can run a lot of interleave a lot of tasks in one thread. So for example, you could wait on the file, and then at the same time you're waiting for the user input, and then at the same time you're also waiting for a file to load in from the OS or the system, and stuff like that. But we'll see how it goes. Let's just get going. Let's begin. All right, so binary application. Of course, when we're done with it, if we ever done with this, I'm gonna send you the IP and the port so you could connect, and then we could hopefully try this live. And let's go. At first, we're just going to use Telnet as a client, just a simple client. Later on, if this works out, we could try in another stream to create a proper client, possibly even with a GUI, possibly using Bevy or Godot or whatever. We'll see how it goes. Anyways, let's see. So, Coda Taco server, I guess. I'm so bad at naming stuff. Let's go. And let's see. So the mission begins, I guess. Let's see if I can figure this out. All right, great. So first of all, we're gonna add Tokio -- full. -- features full. So at first you just add Tokio with all of its features. Then when you want to optimize your application, ship it, you just disable all features and then just enable the features that you have used, basically. That's how it works. So that's why I added right now Tokio, the latest version with all features. That's the first thing. Second thing, we need something to make error handling easier. So I'm gonna be using anyhow for that. The other thing, we need some logging. So we're gonna be going with tracing subscriber. So tracing is just like an interface, in other languages, it's just an interface for logging, kind of like the log crate, if you know that, but it's async friendly and it's much more powerful. So yeah, tracing subscriber is just one implementation out of a lot of implementations that you can find out in the wild, or you can make even your own implementation. But basically, why they're separated? So you can use whatever implementation you'd like, or you can implement it yourself. That's the first thing. Second thing is that for example, like let's say libraries doesn't have to like include a tracing subscriber implementation. They only have to include the interface and use that interface, and that interface basically gives them the functions that they can call to log, like let's say log, error, warn, etc. But then in your own application, you as the user of the library, you have to include a implementation. But anyway, this is just a little thing on why we do this. Anyways, so right now we have tracing subscriber, anyhow for error handling. What's next? We may also need dash map for concurrent hash map, but we'll see how it goes later on. First of all, if you're using Rust rover like me, it's by the way currently free because it's still in preview mode. So if you want to try out Rust rover IDE from JetBrains, you could try it out today, though this is not sponsored. So let's go. I just basically enabled Rust FMT so we can format our code automatically, and I enabled some like the external Rust analyzer because it's much more powerful. Anyways, so that's pretty much it. I guess let's get started coding, I think, if I didn't miss anything. So yeah, so first of all we need to create a TCP server. So, well, there's multiple options, of course, on which servers you'd like. There's TCP, there's UDP, there's even some crazier protocols out there. But since we want reliable messages, meaning that like when someone sends a message, we want to make sure that that message reach its destination. Otherwise we get an error back. So we need a reliable protocol. So we're going to be using TCP. So let's go with some TCP listener here, or let's just call it listener. And let's say TCP listener. Let's see. And hold on a second, I'm gonna close the window. All right, back. Let's go. All right, so if you guys have any questions, let me know. So here we got a TCP listener, and we gotta bind it to some address. Now we're just gonna bind it to localhost. You can see that if you go to the bind method, it actually takes a generic A, which is a 2-socket address. Basically, this is address. And that's basically to allow you to pass like different kind of ways of passing an address. So like you could use either a string, for example, or you could like, let's say, use an IPv4 address or IPv6 address, etc. But for me, I'm just gonna go with the string. So localhost, and then here I could pass in the port that I want. It doesn't matter that much though. There is some things about port that you should know, is that some ports are actually reserved. So hold on a second. Let's see. TCP, or let's just say reserved ports. And let's see. There you go. And here's some reserved ports. For example, let's see, for example, port 80. This one is for Hypertext Transfer Protocol, basically HTTP. It's for web. So if you're going to be making a TCP, like an HTTP server, then you should go with this port 80. It doesn't have to though. It doesn't have to, but this is like the one that is being used for HTTP usually. It uses TCP in version 1 and 2. And as you can see, HTTP actually uses TCP. So yeah, HTTP 3 uses QuIC, I think. But yeah, this is another protocol that HTTP 3 uses. So if you're gonna be using HTTP 3, let's go. That's the protocol you're gonna be using. And QuIC, if I remember, it's a transfer protocol on top of UDP. So basically, there's TCP and UDP. These are the main protocols out there. So TCP is for reliable messages, like for reliable network stuff. So if you send some packet, you're gonna be sure that it's gonna be sent reliably, and if it failed, you're gonna know that it actually failed. That's TCP. UDP is like, it's unreliable, meaning that you just send messages out there. It's like just like a live stream, like you just broadcast, and if someone gets the message or not, that's not your business. You just send the messages. And if they reach or not, doesn't matter, because like, for example, when, let's say you have some network game, right? You have the player position, you would update every frame, so it doesn't matter if like the player position have actually reached the other system. It doesn't have to, because you're constantly given new updates. So yeah, pretty much. And QuizC, if I understand right, it's basically you like reliability built on top of UDP. So like TCP, there's a lot of crazier stuff to make sure, exactly sure that it's perfectly reliable. But anyways, it's basically a trade-off between performance and all sorts of things. Anyways, so that's port 80. So which ports we can use? Let's see. So all of these are kind of like reserved and stuff. Let's ask Google, like, which ports are safe to use? Let's see. Long story short, anything above 1024 is safe, if I understand your definition of safe. Anyway, so I'm just gonna go with whichever number. Let's say something like this, right? So we got a listener, but you're gonna notice that this actually gives us a future, and this future, the output of it is a result. And plus size doesn't really matter. Anyways, so basically in Rust, async, like, it doesn't have an async runtime built in. And that's why we need something like Tokio or some other runtime. Like Rust basically gives us the constructs needed to get going with async, and that's essentially it. So it gives us futures. Futures are basically kind of like JavaScript promises. Basically, it's kind of like a computation, or like, yeah, a computation that is lazy. It's like an iterator, but like it would happen, like that computation doesn't necessarily have the value right now, but you could get the value in the future at some point. If you really need the computation to be done right now, then you could like go ahead and await for that future. So you could stop, not the thread, you're gonna stop the task. So you're gonna stop the task and wait for the computation to finish, and then you can proceed with this task. Because there could be, like in Tokio, it gives us multiple tasks, and like in every thread, and it also gives us multiple threads. So basically you can have multiple threads, and in every thread you could have multiple tasks running at the same time, basically. But I'm trying to explain this more later on, but for now, what I'm gonna do right now is I'm just gonna await this, because I need to know the result now. And I'm gonna so this is gonna give me a result TCP listener, so I'm just gonna unwrap this. But of course we have some problem here. So first, the operator can only be used in a function that returns a result or option. Okay, so this should return a result. Now in Rust, when you make a result, like you have to give it two things. You have to give it like the OK type, and then also the error type. But thanks to anyhow, since we don't really care that much about errors, but we still care to bubble it up, so later on if we want to add proper error handling, it's going to be very easy to do so. I use anyhow result, which is like standard results, but instead of having to give it the error type too, I don't have to. I just give it what is the OK type. And in my case, in the main function, I'm not going to return anything, of course. So I just want to signify that, like, is my program have finished abruptly or have finished correctly. So here, when we end the program correctly or appropriately, we're just going to return OK, and this unit type or this unit value, basically it's kind of like void in other languages, basically nothing, but we're signifying that it's okay, so everything went okay. Now the other thing is await is only allowed inside async functions and blocks, so you cannot use await in synchronous code, in a synchronous function like main here, like, cause you need an async function to be able to await, because you don't have any task at this point, you just have threads. So currently we're not using Tokio, but to use Tokio we could actually make use of this macro that Tokio gives us, and it's called Tokio main. This would basically go ahead, do some boilerplate on our function and modify it to give us the ability to make our main function asynchronous. So there's another error. The async keyword is missing from the function declaration. So as you can see, we also need to make this asynchronous function. Now we can actually use the await function. Now what this actually does exactly, so if we have looked here, it's going to be very weird stuff, right? All of this stuff is happening and things like that. It's just like boilerplate code. But if I want to give you just a simple example of what's happening here, is like, let's say I don't want to use this macro. For example, let's say some other thing or like some other library like microquad or something like that is actually hijacking my main function. So I cannot do this. I cannot change my main function. So what I can do, let me just give you a little example, though I'm not going to give like a very deep explanation about it, but just kind of trying to show you a little bit of an intuition of what's happening in the background. So just going ahead, creating a runtime for you, Tokio runtime basically. So runtime and new dot and this is a result, so let's unwrap it, and basically we're going to bubble up the error using this operator right here. And then this is basically like a builder of the runtime, right? So we could set whatever options we want. Actually not here, actually let's go with Tokio runtime builder, builder. And then here I could say either new multi-thread or new current thread. Okay, so by default when you use that macro, by default it goes with multi-thread, so you have Tokio multi-threaded, so we could use it both for async and multi-threading. Otherwise, if you just want the current thread, you don't want multi-threading, then you could just go with new current thread. But anyways, let's go with new multi-thread. That's first thing. Second thing, we could pass in all of these settings. We don't have to worry much about them, but we could just enable all, because basically, for example, when you await on some or like use some IO resources, like let's say TCP socket or let's say files, etc., you're relying on some weird stuff. I don't want to go in full details, but basically there's like Tokio reaction and stuff like that deals with the OS to make sure that this asynchronous operations are efficient. For example, let's say when you're waiting for a file, you're not going to be just like going in a 100% CPU just waiting for the file every time. It's going to be very efficient. It's going to talk with the OS to make sure that it awakes the runtime when the file is ready and stuff like that. It's crazy, but yeah, that's all you need to know for now. So enable all, and then we can build our runtime. Let's go. And of course this is the result, so let's unwrap it, and there you go. Right now we got a runtime. So but we still cannot use await. Why? Because we still haven't got a async block just yet, so we have to say async.block on. There's a lot of functions on the runtime, as you can see. We're gonna look into it later on, but right now what we need, which is very similar to what the Tokio main macro does for you, basically we're gonna have like basically an async block here, I think. So async move, and I always confuse the order of async and move because it gotta be in this order, so I just remember that it's I am, so There you go, async mode. Let's go. Now this spawn blocking, closure expected to take 0 arguments, but it takes 1 argument. Spawn blocking. If I say, interesting. What's up with this? There you go. Okay, so it actually takes closure. I see. And there you go. So async closure, I cannot do this. Let's just go with this. And then we could hopefully say this. It still doesn't allow that because we have to spawn something, I believe. We have to spawn some task. But as you can see, it's just becomes crazy and crazier and crazier. So for now, we don't really care about all these stuff. We're just gonna let Tokyo do the boilerplate for us. So we're just gonna go with Tokyo main anyways. So yeah. And this would basically make sure to do all that stuff for us, all that boilerplate code. No need. So let's go. So right now we have a TCP listener. Great. Let's try run this. So it's going to compile everything. It may take a little while at first, but then later on it's just going to become incremental. And there you go. So process finished the exit code. You have just bound a TCP listener and we exit the program. Now let's try to accept some connection. So let's accept some connection. Let's say stream is equal to, or actually let's say listener.accept. Listener.accept. Now notice that this gives us a result of a tuple. Basically a tuple is just like 2 elements. In this case, it could be 3 elements or whatever. So here there is a TCP stream and there's a socket address. So, and of course it's wrapped in a result. So let's say .accept, and then this is a future, so we can, or we need to await it in this case because we want to accept now. So we're just gonna wait for our, like the connection to accept some some other peer or something like that. But anyways, let's go with, actually we don't need unwrap here, we could just say this. All right, let's go. So now we're gonna get 2 things. We're gonna get let's see here. Yeah, we're gonna get the stream, the TCP stream in this case, and we're gonna get the what do you call it again? Socket address. Okay, so the thing is, this is also a socket address, but this is the socket address of our own machine, like our server. And the socket address here is for the client that have just accepted our connection, or that have just connected to our server. So client socket ADDR. That's basically it. And just to make sure that this makes sense, I'm just gonna say server socket ADDR, because this confused me in when I was just starting out. So there you go. We could even say .into if we want to. Well, no need. Anyways, never mind. And there you go. So now we have a stream. Great. Let's see if this would work by any chance. So as you can see, our application runs, but there's nothing. Like, seems like the application is just hanging in the air. Right? So what's happening? Well, we're waiting for some connection. So let's grab our telnet. You could use whatever client. I'm just going to be using telnet here. So later on we may want to create our own client, but for now it's fine. Where's the damn thing? Layout. Damn. Where you have gone? Interesting. There you go. Okay. All right. So now let's say telnet, and let's see what telnet takes. Let's see what telnet takes. -h for help. Well, it's --help. And there you go. It's going to give you how you can use telnet here. So what we need. So we need the host and the port. Okay. So let's, and some other options if you need to. So here telnet localhost in our case, because that's our actual address. And the port is 4556. And the port is just arbitrary here. It just needs, you just need to make sure that it's not reserved. So usually port like long, like, what is it called? Greater than 1024, I think. But anyways, let's go with this. And right now we actually have connected using Telnet as a client to our server. And notice that as soon as we connected, the process finished to execute, means that our program had just finished execution. And there you go, we're done. Why? Because, well, we were awaiting for a connection. Once we got the connection, we have just finished the program, done. So here connects to localhost. Here, like Telnet tells us what is the escape character. You could use this basically to close the connection from Telnet itself. So this is basically control and this key right here in your keyboard. And then connection closed by foreign host, because our program or our server have closed the connection once it got it. Great, 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 nice. So what we could do this with connection now, this connection. Let's see. So I guess let's try to read some data, or let's write some data. Okay. So stream.write, write all. There's a lot of write methods right there. Let's say hello. Cannot borrow. So I cannot borrow immutable local variable stream as mutable. It's basically telling us that the stream is not mutable, so you cannot write to it. Right now I just made it mutable. And what's now? So in used write all, that must be oh yeah, so this is actually an asynchronous operation too, so we can await it. So we're basically gonna block the task, not the thread, the task, until we're done with the write. Type mismatch, expected U8 but found str. Yeah, this is expecting bytes, but we have give it a string slice. So what we should do here, we can just turn it into bytes, I believe. So what's up now? All right, so now let's just unwrap the results. So basically, if it fails, we're just gonna end the program with error. And yeah, that should be it. Right now, let's try again. Let's launch our server. And it's gonna wait for a connection right here. Then we're gonna connect to it. And there you go. We have just printed, like it have wrote to us or sent to us hello. And then it just closed the connection. Though, let me just end an end of line here. And yeah, we just got hello. Great. Now let's actually try to read some data and then just write it back to the client. Like read some data from the client itself and just write to it back. This is called an echo server. This is one of the simplest examples here, but let's go. Okay, so stream.read. So these are all the read methods that we could actually use. Though there is a method called read to string and read to end. So let's go with, for example, read to string, and let's create a string here. Basically, this is the client input. Let's say input, and let's say string new. So here we're just allocating a new string, and then we're gonna pass in the immutable access to this read to string function, so we can write into it. So here we gotta await this guy, and then what else? Yeah, this should be mutable, so we can write to it. As you can see, Rust is very explicit about what permissions we give to each function. And finally, if there's any error, we're just gonna do this. Okay, and now instead of writing hello, we could write back the client input that we got from the client. So we could say client input dot as bytes, and there you go. So let's see if this works. There you go, great. Let's try to connect now. And yeah, right now we got input. Let's say hello world, but nothing really happened. Why? Because this read to string actually waits for me until, wait until it gets an eof. an end of stream, I guess, or what is it called? A of end of file, I believe. But anyways, so I could just write whatever, hello world, tokio, whatever. But once I do the use this escape character, control this to close the connection, and then go out of telnet, yeah, it won't work because, well, it did send us back the input, but the thing is we have already closed the connection. So what we should do instead, we want to read line by line, not until the end of the connection, or A off basically. So how we could do that? Well, we want a function called read line or something like that, but we don't have it here. Because if we want that, we have to create, first of all, a buff reader. So how we can do that? Well. Let's create a buff reader for our stream. So stream buff reader. And of course, this is part of Tokio. And there's one thing that you gotta be careful of. Both in, for example, TCP listener and also for this buff reader and stuff, you can see that there's two kinds of buff readers. For example, here there's STD and there's Tokio. You gotta be careful because here the standard library buff reader is not what you want here, because this is not asynchronous. So you gotta be careful with what you use, because the non-asynchronous versions, like the one here in standard library, would block the whole thread, not the task. You probably have been bored of what is you're curious about what is the difference between a task and a thread, but I'm gonna get into it at some point when we need it. But for now, just know that the buff reader will actually stop the whole thread, let's say, but Tokio one would actually just stop the task. So it's async friendly, basically. It's non-blocking. So let's go to buff reader right now. And also notice that even in TCP listener, instead of using std-net TCP listener, which actually exists, we have to use Tokio net TCP listener. Same thing with other stuff that we're gonna see later. Anyways, and also there is these async write ext extension. This is basically an extension trait that you actually gonna need to be able to access this write all function, because it's part of that extension, as you can see here. So to be able to use this function, you gotta make sure to also import this trait. And for reading, of course, you're gonna need this, though we're not using this just yet. All right, let's go with buff reader now. And yeah, look at that. I have actually imported the wrong one, so I gotta be careful. So buff reader, Tokio, and there you go. Now I could go with, hold on a second, buff reader from, and then I could give it my stream. And let's see. So type mismatch expected, buff reader, but found. Well, actually, probably new. Actually, yeah, new. And then you give it the inner, which is in this case stream. All right, great. So right now we have actually created stream buff reader. Now we can have access to more cool stuff, because basically what happens here is that instead of reading byte by byte, this buff reader is basically it basically buffers the input. So for example, here you're watching a stream, right? So instead of sending for byte by byte the stream, what happens is that the actual YouTube server, buffers as much data as it can, as long as it's not too much. But there's a trade-off there. But basically, it buffers as much data as it can, and then it sends it in one batch. That's what a buff reader is. It basically buffers data until it reached some point, some capacity, let's say, until the buffer is full, or we flush that buff reader, then it sends it gets the data, basically. In this case, we're reading from the stream, so we're basically reading as much as possible, then we could, well, anyways. But what's important to us here, actually, at least for now, is that this buff reader gives us some cool functions, or some convenient functions. We could do this without it, though, but yeah. So we have read line, for example. So we could use this to read line by line instead of until EF, which is the end of the connection or like whatever. So here we got buffer, mutable string. Okay, so we need to give it a mutable access to our client input. So we could basically write the data to it. And let's await, and I guess we also need to inwrap. Great. So now we have a little problem though with the borrow checker. So cannot borrow immutable local variable stream buff reader. By the way, is the stream fine? Right, looking good to me. Okay. So here, cannot borrow immutable local variable stream buff reader as mutable. Okay, first of all, this gotta be mutable so we can read from it. That's the first thing. Second thing, we got a borrow of moved value stream. Okay, so let me just build this so we can see a more nicer error, or maybe even we could even like go with clippy. Where's the terminal? There you go. Let me just put it here. Okay, clippy. Cargo C, which is for clippy, and as you can see, it gives us a lot of information about the error. But anyway, this is fine to me. So look at this. So here it says that value have been borrowed here after move. In where? In line 14. So this line right here. And where exactly? In here, this guy. So here where we actually the value borrowed here, value borrowed here after move. Now where this value got moved, this value got moved in this line right here in line 12. And where exactly? In this place right here in stream. So notice that this stream right here is have already been moved here because this new function actually takes the stream as a value, like it moves it, it takes ownership of it. So since it moves it, we cannot really access the stream anymore because it got moved to it, inside of it. So, and here it also tells you that move occurs because stream has type Tokio net TCP stream, which does not implement the copy trait. Because it doesn't implement the copy trait, it haven't been copied implicitly, it actually have been moved. So we cannot use it anymore. So how to actually fix this? So actually, let's see what we're trying to do first here. Well, we're trying to read from the stream, but we're also at the same time trying to write to it, which is actually quite bad if you think about it. Like you're trying to read to something and write into it at the same time. It's kind of meh. So that's something to keep in mind. But there's an easy fix actually here, which is to basically split the stream into a writer and a reader. So how we can do this? Well, so before we actually move the stream here, what we gotta do, we gotta say let stream reader and then stream writer. So we basically got to split the stream into two, into a reader and a writer, so we can actually possibly write in read into the stream, because basically Rust doesn't allow you to read and write at the same time to some value. That like results in all sorts of memory bugs. Anyways, so here we're gonna go with stream.split. So there's all sorts of split methods. There's this one, and there's also into split. Basically this into split actually gives you owned handles and crazy stuff like that, but you don't have to worry about this for now. Let's just go with split. This gives us just references basically. So as you can see, this method is more efficient than into split, but the halves cannot be moved into independently spawned tasks. So basically into split also actually allocates memory for those handles because they're owned. And that's why this method right here is more efficient, because, well, it just gives us actual references. But anyway, let's go with split here. And as you can see here, we got a read half stream reader and a stream writer write half. So we have splitted the stream into two. And so now we could actually, what we can do is in the buff reader here, we can move, instead of the stream itself, we can move the stream reader. So it will take ownership of that stream reader. And then the stream writer, we could use it here, or we could use the stream directly. But anyway, let's just use the stream writer. So here, cannot borrow mutable local variable stream writer as mutable, because we're trying to modify it. So we gotta make sure that it's mutable. And there you go. We have fixed the borrow checker error, which is great. Okay, so now let's try again. Though notice that client socket address, we're not using it, so let's just prefix it for now, meaning that we're currently not using it anyways. So what's next? Let's try to run our server now and let's see what happens. Okay, let's launch the terminal and let's see. There you go. So I have my server running here, I believe. Hold on a second, let's just run this again. There you go. Okay, so I have my server here waiting for a connection to happen. Here I'm going to use telnet. I'm just using my arrow keys to go through my command history. And there you go, telnet localhost 4556. Let's go. Now let's do this. And now we're actually connected into the client, into the server using telnet. So as you can see, connected to localhost, and the escape character is this. Great. Now let's try to write something. Hello. And there you go. We got our hello back from the server. This is called an echo server. So as you can see here, it just have read a line from us, a line of input, which is in this case hello, and it just have sent us back that input. Basically like echo, essentially. But notice that after it have done that, it just closed the connection directly. Why? Because we don't have a loop here. It's like we're just essentially, we're making a TCP listener. We're waiting for a connection. After we got a connection, after the await, basically we split into stream writer and reader. Then we create a string where we can put our client input in. In this case, it's hello. And then we create a buff reader because it gives us this convenience function called readline, and it also buffers the reads, which is more efficient in most cases. And then here we got a mutable. We gave it mutable access to our client input, so we can go ahead and mutate it, which means it's going to put the data into it. And here we await for that to happen. We wait for the stream buff reader to read the line into this string right here. Then after that, we try to write, we use the stream writer to write all. Basically, we write into the client here. We write all the client input as bytes, right? So because client input here is a string, and this write all is expecting bytes. So we just make it into as bytes, and then we await. That's pretty simple. But then after that, what we do, after we have wrote back to the client the input he gave us, we just go here. Okay, so we just exit the program. Done. So to make sure that, like, to make sure we don't exit the connection and keep on like getting input from the client and just sending it back, we can make use of a loop. So here we don't really have to make a new string, and also the buff reader, I don't think we have to. What we really want to, you know, do like forever kind of is reading a line from the client, then writing it all back to the client, echoing it basically. So here I'm just gonna loop basically, and we're just gonna loop this portion of our code. And of course this is a forever loop, right? And here notice that Rust will tell us that this is unreachable code because we don't have any exit condition here. You're just gonna keep on going like that basically, unless if some sort of error happens, of course. So here we don't even need this anymore because it's pretty much unreachable. Let's try this now. Let's run this and let's go. So now if I said telnet localhost, let's write something, hello. And as you can see, I wrote hello and I got back hello from the server. Now let's tell the server, I don't know, async programming is cool. And then notice one thing. Right now, this is what we have wrote, right? But then we got hello, and then we also got async programming is cool. What? And then after we said what, it said hello, async programming is cool, what? Great. Why? Because, well, we're not really creating a new string every time. So like we keep on adding new data. This readline function keeps on adding new data into the string, right? So we just write whatever we had back in memory. So one solution would be to actually create a new string every time, every loop iteration. Every time we want to read the data, we can create a new string. Okay, so if we do this and we connect, now if I say hello, great world, as you can see right now, it's good. The only little problem here, though it's fine, this is fine, but it's not as like performant, kind of. Like not as, basically not optimal. Why? Because every time we want to read the data, we're allocating a new string. So that's not optimal. It's fine, but not optimal. So let's actually move this back to where it was. So let's just put it here, right? But now instead of actually creating a new string, we could just like clear it. So clear the string, so we could get back our data. So here truncates the string, removing all constants. While this means the string will have a length of 0, it does not touch its capacity. Notice this one. It doesn't touch its capacity. So what does that mean? So the thing is, this string, yes, you allocate it, but the thing is, you allocate just some kind of memory, let's say 2 characters or 8 characters or whatever. But once you reach that capacity of the string, you have to again reallocate new string, or not new string, but like new data or new allocation or new back-in memory for that string, which is not as optimal either. So here what the clear function does, instead of like resetting the whole string, it keeps the capacity. It keeps the capacity that we had before, and it just clears the data, right? So it doesn't touch the capacity. What does that mean is that we're only going to be reallocating if, like, in the first time we read the line. After that, like, let's say we got a message of 20 characters, and let's say the capacity isn't enough, then that means we're going to reallocate the string to actually fit that data, right? Correct. Nice. But then after that, we clear. Now the capacity won't be touched, which means we're still going to be having that reallocation that we have done before, which is 20 characters. Now, if the client sent back again 20 characters, we wouldn't have a new reallocation because the capacity is enough. Now, if the client after that sends a bigger message, we're going to keep on doing that essentially. But yeah, that's just something to keep in mind, I guess. It's pretty good to keep in mind what allocations you're doing and how everything is going. Great, lovely. So right now we have created the simplest server ever. Just takes like input and outputs it, like just echoes it to the client. Great, lovely. The problem though with this that we have here, let's see. Let's try to actually right now make 2 clients connect with our server, and let's see what happens. So here we got our server running, waiting for a connection. Great. And now let's try to connect. Okay, great. So client 1 connected just fine. Now let's try to get a second client here. So let me get a second client here. Let's try to connect here too. So telnet localhost 4556, and we actually have connected. Okay, let's see what happens here. If I say here hello in the client 1, we got hello back. If I say hello here in client 2, or hello, we didn't get anything. Why that is the case? Well, the thing is here, if you notice, we're actually only accepting 1 client. That's the first thing. And second thing, like we're blocking on this single client. We still have, like, until now, we're not really exploiting async or multi-threading to some degree, right? We're basically just blocking on 1 client, or just handling that single client. So how we can actually handle multiple clients at the same time? So this would work just fine and this would work just fine, like we have separate clients. How we could do this? Well, we have to use a spawn function. There is a lot of ways, of course, to do it, but let's start with a spawn function here. So let's see. First of all, we need to actually keep on accepting new clients. That's the first thing. And actually, hold on, go back. I forgot to show you something real quick here that is important for the explanation. Where's my terminal? Damn, come on, let's go. There you go. Okay, so let's connect again real quick. Okay, let's say hello here. Let's say hello here. And now let's try to disconnect from this client. And connection closed. And as you can see, we still didn't get any kind of any kind of output here, because actually we're not really connected. Telnet is telling us that it's connected, but it's not really, because we're not accepting any other connections here. So yeah. Now let's actually handle multiple connections. So let's say loop. Great. So now we're constantly trying to accept listeners, but we also have this loop right here, which would block, right? So we will never go back to the start of the loop to actually accept again. So we need to actually run this thing right here, or actually this whole thing, right? We need to run it in its own thread or its own async task. So how we could do this? Well, we can say, well, what is it called again? Yeah, Tokyo spawn. All right, so here we got a future. So async move. There you go. Great. And now we could actually take this code right here and put it inside Tokyo spawn. Now this Tokyo spawn, there is two options here that could happen. It will either go ahead and spawn a new thread, a whole new OS thread. Though don't worry, that wouldn't be like a very heavy thing, because in fact Tokyo under the hood is using a lot of cool optimizations. Like for example, for threads, it's using a thread pool, which means at the start of it all, after the start of the runtime, when you create the runtime, it actually creates a thread pool, which basically contains a collection of threads like ready for Tokyo to use. So you wouldn't have to actually wait here for a new thread to be created and stuff like that. Otherwise, what could also happen is just it will run on the same thread, but like on its own task, right? So, and if it's on its own thread, then it's actually going to be in parallel, like they're very separate, in separate worlds, like they're in separate computer or processor or whatever. If it have spawned in another task, that means that whenever you on another task but on the same thread, what's going to happen is that when you call await, what happens here is that you're giving back control to the Tokyo runtime. At this point, when you await, you're giving opportunity. So here you're basically waiting for something to happen, but at the same time you're giving back the control to async, so like to the Tokyo runtime, so you can actually give the opportunity for other tasks that are running in the same thread to basically run, right? So yeah, I just gotta be careful about that, and we're gonna explain that further here. But anyways, that doesn't really matter if it's gonna be in a separate thread or in an async task in the same thread. Doesn't happen. Tokyo handles all of that for us, all that details for us. Though, of course, if you created a Tokyo runtime that is only single-threaded, then of course it would be on another task, because there will be no other threads. But anyways, that's just a little explanation right here. Okay, so what is happening? First of all, we cannot actually use this operator anymore because we're in another function altogether. We're not in our main function. So for now, let's just keep it simple and just in wrap. So basically, if some error happens, we're actually not gonna crash the program. Well, normally this in wrap would crash the program, but in this case, since it's running in its own task or even thread, what's gonna happen is that it will just kind of crash this Tokyo thread thing. And how you could detect that is by basically this Tokyo spawn gives you a future, I believe. Actually a join handle, right? So a join handle. And then basically you could use this join handle to do all sorts of things on this task that you have just spawned, because this task will actually run asynchronously or even in parallel. So at this point, like Tokyo spawn, after it created this task, it would just return immediately. So you won't wait for all this craziness to happen in this loop and stuff like that. This would happen on another, like asynchronously. And then in this thread or this task, you have the join handle, which you can use to do all sorts of things on the task you have just spawned. You could like await it, so basically wait for it to finish. Or even abort it, like cancel it basically, and all sorts of interesting things. You could possibly even kill it, I guess. Yeah, it's basically abort, I think. Yeah, it's abort. So abort the task associated with the handle. Yeah, there's all sorts of cool things that you could do with this. But in our case, if you want to like handle errors, we could say await in wrap. But be careful here, we're actually going to be blocking this loop until this finishes so we can handle the error. So for now, just to keep it simple, we're not going to actually do that. We're just going to, run, like spawn the task and just forget about it for now. Later on, we may want to deal with that later on. Anyways, so right now what we're doing, we're looping. We're constantly looping. We're creating a new connection, like we're waiting for a connection to happen every time, synchronously here. And then once we got a connection, what happens? We spawn a new task for that specific connection, which makes its own loop and stuff like that. So it runs separately. And then after we spawn this task, we immediately go back to listening for a new client instead of like accepting a new connection, instead of waiting for the client to do its stuff and disconnect. So this should do the trick. Let's see. So we have run our task, like our server. And let's see here, we get telnet to connect, and now we're gonna get a second client now. All right, great. Let's see if this works. Hello, and let's say hello here. And as you can see right now, both clients are connected at the same time in our server, and both clients are running at the same time. Like basically, this is separate from this, is running its own task or maybe even in its own thread. So they're very separate. So that's pretty cool. That basically means that this wouldn't interfere with this. So that's pretty cool. All right, lovely. So what we could do next, now we actually have done a pretty minimal, like I think the smallest server that like not fully correct. We still got to handle, for example, what happens when an error happens in one of these guys and stuff like that. But yeah, essentially this is functional. So that's very nice. Great. So what we could do now, let's see. And notice one thing here, we got async move. And why we need move? Because without the move, you cannot actually use some things. So as you can see, async block may outlive the current function, but it borrows stream, which is owned by the current function. Okay, so what this is telling us, it's telling us that this async block can outlive the current function. Or actually not really even the current function, but it can outlive this block and stuff like that. Anyways, what that does mean, basically, what's happening here is that here we have the stream. This stream will live for this specific block right here. Once you exit this block, the stream will go ahead and destroy itself, so it won't exist anymore. So what's happening here is we're spawning this task, And this task, of course, won't get destroyed or canceled once we exit this block. It will keep on going in the background. It's like a background task. In fact, it's a background task, kind of. So what happens here is that since we're currently trying to use this like we're borrowing this stream, but this could outlive. So when we exit this and we go back, or exit this entirely, or even exit the program or whatever, what's going to happen is that this stream would get destroyed, but this task is still using the stream, which is going to happen in a sigvault because this won't be valid anymore, or anything could happen. It's indefined behavior. Other programming languages wouldn't really care. Like, you would just you just have to learn the hard way. But here, since we're using Rust, it's not gonna make that, like, allow that to happen. So we gotta use move. What move here means is basically we're gonna move the ownership of this stream to inside this task right here. Okay, so essentially we're going to transfer ownership. Like, basically ownership is like who's responsible to destroy something. So the stream here, who's responsible is this kind of block, right? This block right here. Once it's out of scope, done. But once we move it to this task, which means that this task is actually right now responsible for destroying this stream, which means, well, it's just gonna keep it around here. So anyways, so that's great. And why we need this? Because this would run in its own thread. I mean, it could run in the same thread, which would be fine, kind of. But, well, you gotta handle both cases, because this could be in its own thread, or it could be in the same thread but asynchronous. But anyway, let's not get into those details right now. So, alright, so what's next now? So let's see. So basically right now what we want is we want to, instead of just like, right now our server is kind of useless to some degree because we're not really doing anything interesting. We're just echoing back the data that we got from the client. Right now we want to actually broadcast this data to all the other clients, really. So how we could do this? Now you can think about possibly making a vector and stuff like that, but that wouldn't work. I mean, that would work, but you need the mutex and stuff like that. But the best way to go about this actually is to go with something called a broadcast in Tokio. It's a message passer. But anyways, let's see how we can do it. Like a message channel, right? So, alright, how we can do this. So let's make a message passer here, like a broadcast. A channel, I guess. Not sure what to call it just yet, we'll see. And let's go with a Tokyo broadcast. Oops, that's called I believe broadcast. And is it really called broadcast though? Let me search it up in the documentation. Tokyo docs, let's go and let's look for broadcast. And there you go, it's inside sync. There you go, it's a multi-producer, multi-consumer broadcast queue. Each sent value is seen by all consumers. So let's go with this. So it's not STD, but let's go with Tokyo sync broadcast. And let's go. Let's actually create this now. So channel, and this is a bounded channel because there's multiple kinds of channels. Well, the main ones, I mean. There's a bounded channel and there's an inbounded channel. There's inbounded channel is basically, it doesn't have a limit, just like a vector, for example. It would just keep on growing until you run out of memory, which would be not good. You know, it's like anyone could just like attack you and just keep on sending you messages and spamming messages, and yeah, your server will run out of memory and everything will go into chaos. So always use as much as possible like bounded channels, so you can get a limit, and basically what happens when you reach that limit depends on the primitive that you're using, the sync primitive that you're using, like depending on the channel, etc., etc. But I think for broadcast, I think it would probably just block the task until you have enough space. But yeah, anyway, for now, let's just say whatever, let's say 32 messages maybe capacity, or whatever. You could set this to whatever capacity you'd like. Anyways, let's see right now what we got. So type annotations needed. Right now Rust doesn't know exactly what's happening here, like what is this, like what type this channel would be receiving, what type it would be sending, etc. And notice that it actually gives a sender and a receiver. Now usually people would actually say TX RX like this. Basically this is the sender TX and the receiver is RX. Though I'm honestly just gonna go with, let's say, message sender. Fine. I'd like some readable names, and the message receiver. Now let's see. Now when we get like some sort of input from the client, let's actually try to broadcast this. So how are we gonna do this? Well, let's see. So stream buff reader, stream writer. So after we read data from the client, instead of writing data, right now I'm just commenting it out so you can kind of see what changes we have done. Or let's just remove, actually, fine. We're not gonna write back the data, like we're not echoing it back anymore. Right now we're gonna try to broadcast it to other connections, to other clients. Let's see how we can do this. Well, let's say message sender dot send. And here we can send whatever data we want, some value t, generic. Of course, you gotta have the send trait, you gotta implement the send trait. So it can be sent, basically anything that implements send trait is capable of moving from one thread to another, which actually we need because the other clients and the server itself is like in another thread, like, or task. Anyways, let's say dot send. In here, let's send our client input string. Let's see what's gonna happen here. And use of moved value, message sender. Let's see a better kind of compile thing. And notice here that again the borrow checker kicks in, and let's see what it all does. So borrow of moved value client input. So it's telling us that we're trying to borrow some value that have already moved. Well, first of all, where we're trying to use or borrow that value, we're trying to do this. So let's see, value borrowed here after move. So here, client input dot clear. In here, we're trying to borrow the value, and where it's the value have been moved, it have been moved in line 25 in message sender dot send client input. So when we say send, we're actually moving the data to the other thread. We're moving the ownership, which is not what we want. Now here, there's a lot of ways that we could do this. We could achieve this, but in this case, I think it's fine to just clone the string and just give back, give a string copy to other threads, essentially. So yeah. And now what's wrong with this? Let's see. So I think right now we have solved this issue of the string. We're just cloning it. And what else? So move occurs because message sender has type Tokyo sync broadcast sender string, which does not implement the copy trait inside of this loop. So it's telling us which loop it is. And here it says that use occurs due to use in coroutine. Coroutine is kind of like task, basically. It's essentially a task, I think. So value moved here in previous iteration of the loop. So essentially what's telling us here is that we're moving the message sender here, but we're trying to use it again in other tasks. So we're trying to use it from other tasks. So to be able to actually use it in multiple tasks here, we have to clone this message sender. And actually cloning is what should happen here, because basically cloning sender is very cheap, you know, and it's actually what you need to do. So like every like in every channel you have receivers and senders, depending of course on the channel. But broadcast is, I believe, a multi-producer, multi-consumer, which means you can give a sender for like multiple threads or multiple tasks, and you can also give a receiver for multiple tasks, and every sender could, like every thread or task could use its own sender, etc. So here let's clone a sender for every single task we have. So let's see, client message sender, and let's say message sender dot clone. Again, this is a cheap operation. In fact, this is what you should do. Power of moved value message sender. Consider cloning the value. And let's try again to go ahead, and instead of using the message sender itself, we're going to be using this guy. We're going to use our own copy of the sender here. And there you go. Right now we don't have that error anymore, but we'll notice that it used results because this actually gives us a result. But you gotta be careful because what the result is here. So it returns on success, the number of subscribed receiver handles is returned. This does not mean that what's happened there. Subscriber receiver handles is returned. So if it's succeeded, it tells us how much subscribers, like how much subscriber receivers we have. This does not mean that this number of receivers will see the message, as a receiver may drop or lag before receiving the message. Okay, let's see. And otherwise it gives us a send error. So attempt to send the value to all active receiver handles, returning it back, it could not be sent. Successful send occurs when there's at least one active receiver handle. Okay, so basically this would give us back our value if no one have got the value, like no one is interested in the value. So for now, that means that no one is interested in the value, so that's fine, that's acceptable. If no one is interested in the value, who cares? So we don't really need to unwrap that, actually. And yeah, now let's see. But the thing is, no one is using message receiver though. So no one is actually receiving messages. So how we could do that? Well, someone have to receive the message. Well, who should do that? Well, the clients should do that. When a message is sent, the other clients should receive it and display it, basically. So how we could do this? Well, so the thing is, here we have a little problem, but let's just go with it. Okay, let's just go with this. So here, buff reader, we're gonna send, and let's try to receive. So message receiver, but again, we cannot really say message receiver because we have to clone it first. So let's get our own, like every client should go get its own sender and receiver. So let's say message receiver dot clone, and here actually there's no clone, because for this particular, this would work for other channels or most other channels, but for this particular channel, I think you gotta do I believe client message sender dot subscribe. Yeah, there you go. Okay, so here creates a new receiver. So basically you're telling it which sender exactly you want to subscribe to. Creates a new receiver that will receive. Interesting. So send will not be seen, and then after we subscribe, there you go. Great. So actually what we're doing, not this, we want the message sender itself. So message sender, message sender dot subscribe. So we gotta subscribe for the broadcast. And what else? And now here we could actually use our client message receiver to receive messages. So here we could say, I think receive, right? Yeah, there you go. So there's a receive function here. There's also some other functions, but basically this receives the next value for this receiver. And this would actually give us an option, I believe. Result, string, or receive error. So receives the next value for this receiver. Each receiver will receive a clone of all values sent after it has subscribed. Error, received close. So if the receiver, like the sender got closed, we're just going to get this error, I think, is returned when all senders' halves have dropped, indicating that no further values can be sent on the channel, meaning that, well, the channel have been closed, basically. So this is basically a result. Okay. So let's see. So if let, I believe, okay, some message is equal to client receive. So what's up now? Cannot borrow immutable local variable as mutable. So we gotta make it mutable. Okay, so now what we get? Expected future found. I think we gotta await this, correct? Let's go. So we gotta wait for this to happen. And then after that, if it's everything went okay, and meaning that there's still senders, like there's still like the channel is still open, we're just gonna get the message. So here we could basically, you know, print the message, I believe. So let's see how we could do this. I think print line. Yep, let's go with that, I think. And let's see. Well, actually, we could just do this. And let's see what's gonna happen now. We have a little problem here, but we're gonna see later on. Stream writer. Okay. So we're not writing anything to this to the server. So, anyways, let's see here what's gonna happen right now. So let's first of all run our server, and let's try to connect here and connect here. Let's try to say hello here. Great, but we haven't got any message here. Let's try to say hello from client 2 here. And we still haven't gotten anything. Interesting. Actually, I think we gotta write to the stream, right? Oh yeah, my bad. My bad. We don't want to write it in the server. Let's say stream writer dot write all, I believe. Yeah. And let's write the message that we got here. And of course, let's unwrap or await, and then basically unwrap. And let's try again. And what's happening here? So yeah, this should be as bytes here. As bytes. And let's go. Let's try now. And notice here when we actually cloned it, we have transferred ownership to the send. And the send basically transfers ownership to here, right? So the message gets transferred to this scope right here. And here we got the message. But anyway, let's see what's happening here. Just time must be known at this point. Write all. Consider giving client message sender explicit type word placeholders are specified. Client message sender. Okay, so it wants to know what kind of message we're sending, what type of message we're sending. Let's tell it explicitly that we're gonna be sending a string, I guess. Not really here, actually. Yeah, no, not really here. Let's say here. Let's say sender, and then let's say string. Or actually, let's just go here. Let's go here in when we create the channel. Could just give it the string as in turbofish syntax. Like not string, but like the message type that we're gonna be sending through this channel. It just gotta be send. It gotta make sure it actually implements send, which string does. Because if you see here in channel, hold on, what? It's actually clone. Alright. Well, clone I think also implicitly have send. But anyways, whatever. Let's try now. We're launching the server, and let's see now. Great. Let's say hello from client 1. Okay, nothing happened yet. We don't see any messages. What if I say hello from client 2 now? Well, that's interesting. That's unexpected. By the way, for login purposes, I'm gonna make sure to... Oh, we're not using the message receiver. Interesting. Which? Why? Interesting. Resubscribe starting from the current tail element. What if I said resubscribe? Let's try again. That's interesting. I'm probably forgetting something here. Interesting. Okay. If I subscribe first, just to make sure. And what we should do now. Interesting. Let's see what we have done wrong here. Well, first of all, let me just... Oh, why we have this weird stuff? Okay, anyways. Let's say it's not a CD. Let's say tracing, I think. Tracing subscriber, FMT. Here I'm just gonna bring in the logger. So init. That's how you initialize the tracing subscriber logger. Forgot to initialize it before. But yeah, nothing interesting happening just yet. But here I can hopefully say log. So, well, let's say print. Actually, no, tracing subscriber log or print. Yeah, what? I actually forgot how to do this. Interesting. Yeah, tracing, my bad. And here I believe, yeah, there you go, info. So there's info, warn, error, debug. And let's just say stream buff reader. Let's say read it client or read client input, and let's see, else haven't got a message. And here maybe I'll say have got a message. And let's see. Am I awaiting this actually? Oh, I guess I don't have to. Yeah, I think maybe I don't have to. Yeah, no. Alright. Let's try this out real quick. Okay, so as you can see right now, it's telling me that it read client input the server from the server. Great. So now let's try this. As again, you have read some client input. Nice. Okay. Interestingly, it doesn't read any client input. I've got a message. Yeah, it's waiting for what? Yeah, I think it's waiting here in the client message receiver. It's still waiting for some, I think, some input, because they haven't told me have got a message or haven't got a message. So yeah, it's still blocking on this receive, seems like. So yeah, I'm doing something wrong, or like I forgot something, I believe. Let me make sure I'm using broadcast here right, because it's kind of interesting. So here what you say, broadcast channel, you get rx1 and rx2 tx.subscribe. Okay, rx, so here we got tx.send, so we're sending some data here, and then here we're receiving data in rx1, and then in rx2, here notice that we use tx.subscribe just like we have done here, here message sender or subscribe. Great. So then here we try to receive, await, then we unwrap. Interesting. Okay. Not sure what I'm missing here. Handling lag. The receiver lagged behind. Interesting. We don't really need this message receiver. We're already subscribing for everything here. After this call to subscribe. Client message sender. I'm probably doing something stupid here and I haven't noticed. Send client input. So yeah, we're getting red client input, then I think it's blocking here for some reason. Interesting. Interesting. Client message. Let's try to do this first, maybe. Say tracing info, waiting for client message. Let's go. Let's try again. See what's happening there. This is interesting. Great. Hello. And notice something. I've got back my message. Interesting. Let's say here world. Okay. All right. Right now it's actually working. Great. Great. But notice the one little thing here is that we're getting back our own message here. And oh, I think I know now what's happening. Yeah, I think I know what was happening. Interesting. I mean, there is another problem that I didn't want to fix right away, but this one wasn't expected. But it's nice for everyone to learn from my mistake there. So X, and we got world. Y, we got world, and stuff like that. So everyone gets his own like copy of the string. But let's see. So the problem that we have here, first of all, is the fact that we're receiving our own message. So how to fix that? And by the way, I have fixed that. I fixed the previous issue by first of all sending my message and then waiting for the receiver. Before I was receiving first and sending. I'm not sure what really exactly happened there, but I think maybe some sort of deadlock or something. I don't know. I'm not sure what happened exactly, but let's see. So here we're just gonna make sure that we're not sending the message to ourselves. So what we're gonna say here is basically so here we got the client socket address, right? So we could use that to check if we are the actual client's socket address. Okay. So the thing is, yes, we got our current or our own client socket address, but we don't know who have sent the message. Who's the client who sent the message, I think. Yes, the only thing that we know. Hold on a second. Well, actually not here. We want it here when we receive the message, here where we need to actually filter it out. So here we only know the message itself, but we don't know who sent it. So what we're gonna do, we're gonna make a actual struct. We could go ahead and like just say string and here say socket addr in a tuple like this too. That also works. Otherwise we can make a use of a like a struct. But let's just go with this one first. Let's see. And make sure it's the correct one. I think std.net is fine probably. Yeah. This one is for Unix only, I think. Anyways, let's go with this one. Just for the standard library, doesn't matter. And what else? Now here, instead of just getting a message, we're gonna get the message and the client who sent the message. Message client. So we're getting both. The other thing is that right now when we send our message, we also gotta send who sent it, which is our own socket address. So client socket addr. Great. Nice. Now let's see. So now we're not actually using the message client just yet that we have got from the sender. Or we could even say, but anyways, fine. So now what we should say, I've got a message, blah, and now, yeah, let's say message client. Let's compare the message client to our own socket address, basically, or actually client address, right? So client addr, and what we call this client socket addr. Okay, client socket addr, fine. Now, basically, if say if message oops, message client socket addr is equal to our own socket addr, which means the client socket addr. Then at this point, we're just gonna, you know, I'm not sure. Let's just say this actually for now. Let's just, oopsies, don't need this. Well, actually, yeah, we could just say if not. So if not, then we're gonna write the message. So if the client who sent the message is different from us, so basically not us, so we can avoid, you know, that kind of, what is it even called? The kind of loopback, or like, I forgot what it's called, but basically what we have created before, echo, yeah, the echo. Anyways, let's see right now what we got. Let's create a server, or let's run a server, and let's run some clients now. Now we got 2 clients connected. Let's see. Hello. Great. But we still haven't got anything here. Let's say world, maybe. Hello world, okay? We still haven't got anything, interestingly, here. I know why, but let's just go step by step. Let's say code taco here. And notice that after I typed code taco, which is my message, then I got the hello message from the other client. If I say something else, I'm gonna get my second message. If I say another thing, here I'm not gonna get anything because there's no message left for me to consume for this client. But here right now, if I go again to this client and say something, I don't know, cool, then I'm gonna start to get my messages that this guy sent. So notice here that we're actually waiting for we only receive the messages once. Like, first of all, we receive it only after we have inputted, we have gave our input, our message, we have sent one message, then we receive one message. That's the first problem. The second problem is that we're receiving one message after the other instead of all the messages that we have got so far. So let's solve the second problem first, which is that we want to get all the messages that are currently in. So how we can do that? Well, instead of if let okay, we could set while. So while there's some messages, we can basically print it. And we cannot see else anymore, doesn't matter. Let's try this one now. So now we should get all the messages that are available. And let's see. We're gonna have a problem, I think, here. Yeah, we're gonna have a problem. Well, let's see first. So let's say hello world. Let's say here code taco. And we got one message, interestingly. And the problem with this, though, with this kind of way of doing it, is that you're gonna be waiting for messages like all the time until the channel is dropped, which is not what we want. We want to wait for the messages that are actually currently in. So how we could do that? Well, instead of receive, we could say try receive. Try receive, and then there you go. Okay. So instead of just blocking when we don't have a message, we block until we got a message. Right now we're just try receive until we got a message, essentially. But anyways, let's see. Let's get our clients on and let's see. Hello world. Now let's do something here. Let's send something. And notice right now we actually got 2 messages at the same time. So basically all the messages that we have got from the client at the same time. Before we had to like write 2 messages to actually get 2 messages. So yeah, that's the second problem I got fixed. Now let's fix the first problem, which is the fact that we're actually like we only give the client a message after he sent a message, which is not what we want. We want these two operations of waiting for the client message and waiting for the client input to happen at the same time. So whoever comes first, you know, gets control. So how we could do this? Well, there is something called select in Tokio, or in fact like async in general. Probably your executor would have that, but anyways, let's see. So as you can see, Tokio, select, it's a macro basically. Now actually there's two ways of doing this. I think we could probably, I never really tried this one. Well, like you can just basically spawn this guy, just like we have done here. We could spawn this client input stuff and then this waiting for client messages in another thread and stuff like that. But I think this is bad, not bad, but like suboptimal. Because well, the thing is the client input like wouldn't happen like very much. Like most of the time it's just gonna be very much waiting. Same thing for client message, because here you're bound by the user. The users, like humans, are super slow at sending messages and typing, etc., and also network and stuff like that, whatever. So here we're gonna be using the send. Let's see something. So basically you give it patterns like this. You give it the async expression, and then optional if precondition, and then a handler, essentially. And then it runs both things, like, and whoever matches first gets to you know, to do its own task right here, to run its own handler, and the other tasks that are in the select or the other patterns or whatever you want, like the other handlers just get dropped, like the other futures async expressions get dropped. So that's nice. So how we could do this? Let's see. Let's try to do this. Select. So first of all, this is a macro. So let's see how we can select. And first of all, we need the pattern. So pattern. Believe it or not, I actually don't remember how to use this. Interesting. Is there some example here real quick? Yeah. I think we could just do this, right? Yeah, I think we could just do that. Because we just want to wait for any one of them to happen first, essentially, I think. Or like you could say some V. Interesting. Anyways, I think what we want here is just this. And then we want to basically, in this case, wait for this guy for reading a line from the user or from the client. Actually, that's not how it should be equal here. And then we need a handler. And of course, notice that I don't need no wait here because I shouldn't actually put it. It would happen like by the macro. So instead of this stream buffer reader read line await, we're just saying stream buffer reader read line. And what else? Let's try the other thing now. The other thing that we want to also run in parallel, try receive. Now honestly, receive is probably fine here because it's gonna get dropped anyways. So client message receiver, let's just go with receive here. I'm not sure it is correct. We're gonna see how it goes. And for now, we're just gonna do this, I believe. And let's see. So right now here, whichever comes first, it's gonna run. And after that, all the other things will be dropped. Then we're gonna go to the next iteration of the loop. Let's see if this works by any chance. So right now we have run the server. And let's see, hello. And yeah, we didn't get any input, interestingly. But if I say, ooh, all right, so this actually doesn't work, interestingly. Oh well, fun time. Let's see what I've missed again. Select, read line. Oh, no, this is for streams. Seems like interesting. Streams are just like async, like iterators, but async. Those are what streams is. Right. A is none. Interesting. Operation timed out. Oh. Interesting. I forgot the actual handler code. My bad. So let's see. So after we got some message here, essentially, and yeah, this should be okay. Well, yeah. I think like this, correct? Yes. Nice. Great. This is the first one. And the second one, read line, I don't think it gives us anything. Isn't it? But we still have to send the client input stuff, right? Because read line just mutates the client input here. So, yeah. And let's just copy this one here. And this is the handler. So if we read some line, we're gonna, execute this block. But of course, like once you get into this block, it will just keep on blocking, like, and the other futures won't get to run anymore. And in fact, it would be dropped once we're done with this. Anyways, so here we're gonna, of course, check if there is some of this thing. And let's go. And there you go. I think they should do the trick. Let's see if this works. And let's say hello. And let's go. Hello, let's go. Nice. All right, let's go. Great. And of course, if you do send messages here, let's go. Amazing. So right now it's actually working. So what's happening here, we're kind of like multiplexing using the select operation here on the read line and the client message receive. So basically we're waiting for both features to happen. So like we're waiting for the read line to happen. So we're waiting for the client input, for the user input. And at the same time, we're also waiting for the client message to be received. So whatever happens first comes to run first, and then we just drop the rest. So like if we have got some input from the user, then we're just gonna run the handler of that read line. And after that, we're just gonna, quit the select, and we're just gonna go back on the loop, client input clear, and so on and on, basically. So that's pretty cool, though. Honestly, just to make sure, we're gonna clear actually after we're done with the client message. We could just do it here, just to make sure. This should be the exact same thing, though. Should be the exact same thing, just a bit differently. So yeah, lovely. So right now we kind of got I guess a chat server running right now. It's multi-threaded, asynchronous. So that's pretty interesting. So we don't need all this stuff anymore, which is nice. The other thing that maybe we could improve this with is the fact that right now we're just printing the messages, but we don't know which client have sent it. So I guess for now, what we could do, we can, let's see, we can, yeah, we could use the, where is it? Hold on. Yeah, the socket address. We could use the socket address that we get from the message to show which client has sent this message, for example, as a simple thing. So have got a message, great. Let's see. So instead of have got a message and stuff like that, right now what we could do is so here we're writing all the message to the stream, great. So instead of writing messages bytes, we could like create a new message, kind of. Or honestly, hold on. Yeah, let's just keep it simple and let's say new message. Or let's just shadow the old message, I guess. Or let's say formatted message, right? Let's say that. And here we're gonna use the format, though this would create a new string. But anyways, so let's say for example this, and the first one would be the who sent the message, so message client socket address, and the second one would be the message itself. Great. Now instead of the message itself, we're gonna go with the formatted message as bytes. Let's try this out. And let's see what's gonna happen. Hello. And look at that, right? So this is that client. So hello world, I am client 1. Look at that, great. But if we send message here, hello, notice that these IDs are different. Look at that. So 48760, this is the client 48760, this is the client 48772, which is pretty interesting. Nice, lovely. All right, so now what we should add to our chat server. Currently we have got some minimal functionality in, like multiple clients can send each other messages. And yeah, that's pretty cool. And each client, like each message have like its own kind of client ID and stuff. I think the first thing that we could maybe improve this is to like each client can like assign itself some sort of a name. So instead of showing this weird ID thing, we could like use the name of the client. So there's of course a lot of ways to go about this, but let's just see some simple way of doing this. Let's see. So after we have accepted the client, okay, so where we do this, we're doing it here. Okay, so what we could do here is we could, like, after of course we're getting the stream writer, of course after spawning, because we don't want this to block like connections until the user or the client tell us the name. We want to put it into the spawn function here. Okay, so after we create the actual reader, I think, yes, let's go with that. And after this, so here, let's wait for the client, like the first message is going to be from the client would be the name that it wants, or basically. So let's see. So client, well, not client, stream buff reader dot read line. We could just reuse our client input. So there you go, no problem. Of course, we gotta make sure to clean it up before we go to the actual loop, I think. So yeah. Now here, what's going on? So unused. So let's actually await for the client to give us some input, some line. And what's after that? Yeah, this can fail. So let's say in wrap. And there you go. Right now we have read a line from the client. Great. So what's next? So let's actually use this line as the name for the client. How to do this? By the way, let me see one thing. So this is all the stuff that you could get from the socket address of the client. You could get the IP. So you could use all sorts of things. You could get the port of the client that is connecting from. You could know if it's like connecting through IPv4 or IPv6. You could set the IP, change the IP address associated with the socket address. Interesting. FMT, clone into string hash, so you could like use it in a hash map and stuff like that. To socket ADDRs, converts this object to an iterator of resolved socket ADDRs. Interesting. I don't know what this one particularly does. With current subscriber, this is just tracing stuff, and then we could actually also set the port. And this is also just tracing stuff for login and stuff like that. Anyways, so what we want to do here, I'm trying to think of the way that we're gonna, because there's a lot of ways. Let's see. So you could use, for example, a hash map where the keys would be the actual stream socket ADDR. Or otherwise, we could send it the name with every message. I think let's go with the hash map way. Now, the problem though is that you cannot just use any hash map, right? So like hash map is actually it's not meant to be used for multiple threads or multiple tasks, async tasks. So basically it's not meant to be used asynchronously. And actually Rust wouldn't allow you to do that. So, but we could do that using an arc if we wrap it in an arc in a RW lock or a mutex even. So let's start with that, though I'm going to show you a more robust way of doing this, I think. Let's see. So let's say call this names, I believe, or client names or whichever. I think. So client names is equal to what? To an arc, let's say. And of course, this is a primitive in the standard library. So import it. There you go. And after that, we want so why an arc? An arc basically is like a reference counted, but it's atomic. So atomic reference counted. And this arc would allow us to share the ownership of this this hash map or whatever inside of it actually with all the threads, basically all the tasks, right? Asynchronously or multi-thread, doesn't matter. So basically like across, so all threads would basically kind of like, or like all the threads that have cloned the arc would have like shared ownership essentially. And yeah, right now we need another step, but let's just go with the hash map here for a second now. And actually, let me show you even the error that you would get. So without an arc in the first place, just so you can kind of know. All right, so here we got a simple hash map, nothing crazy there. Great. So what we should do now? Let's see. Well, I want this client names to persist, not like to persist between clients. So in fact, I'm gonna do it here, not inside the client, like the accept connections loop. So here and now, let's say client names dot insert. So we're gonna insert a new key. Let's say the key would be the client socket ADDR. We could use the whatever. Let's use the client socket ADDR since it actually implements hash, or we could use it as a key. And what else? So, and here we could say the name of the client. So, and actually, we're actually gonna get the client name here. We're getting it here as the input. And just so I don't forget, I'm also gonna make sure to, oops, not here, here. And I'm gonna make sure to actually clean up the client's input after we're done with it, just so I don't forget. And now here I could say this, right? So client name, insert client socket ADDR, and now we're just gonna get the client input. Though I'm just gonna trim it though. Trim it. And let's go though. Let's just say client input. Well, it's fine. Let's say trim, and then we're gonna clone it. Gonna clone the string. Great, but we're gonna notice something here. And let me show you the whole error. And notice this. So cannot borrow client names as mutable. Okay, well this is simple actually. Let's go with here mutable. Let's make the hash map mutable so we could actually mutate it. Now the actual real error here. Client input does not live long enough. This is the error that you're gonna get, and it's gonna tell you all stuff about lifetimes. So lifetime one appears in the type of client names, binding client input declared here, blah blah blah. Argument requires that client input is borrowed after blah blah blah. So here it's telling us that the borrow value does not live long enough. Here we're using it in client input dot trim here. Actually, hold on, which? Yeah. So why this is the case? Basically, we need that thing. What is it called again? Yeah, we need to make this into an arc so you could share the ownership. Though I'm not sure it's actually talking about the client message itself. But I'm not really. Maybe I'm doing something wrong. But anyways, so here it's telling me that after I added the arc, cannot borrow data in an arc as mutable, because anything inside an arc is actually immutable. But how can we mutate it if it's immutable? We're gonna need some sort of synchronization first, because, well, if we, like edit the hash map for multiple threads, then we're gonna have an issue. Because, well, we can have like data races, and then basically the data can get corrupted. Like if a thread, like multiple threads tries to read and write at the same time. So basically you need some sort of some way to synchronize the threads together so they don't step on each other's toes. That's first thing. Second thing, you need some way to mutate from the arc. We're gonna use intermutability. Now, there's two simple ways of doing this. Of course, there's a lot of ways, but the most common is gonna be the mutex, and the other one is the RW lock. Okay, so these are basically synchronization primitives that you can use. These are in the standard library, both in the standard library and also in Tokio, or stuff like that. But basically what these do, the mutex allows you to lock, allows a thread to lock it. And once it locks it, it basically kind of like, it's like it have it, basically, it like got exclusive access to the data that you locked, that is inside the mutex basically. So here, like the hash map, the thread would go ahead, lock the mutex, and if it's not locked, like some other thread have blocked before it, it's just gonna take the lock guard, and then it could do whatever it wants with the data. Like for example, here in hash map, we can actually go ahead and mutate it and do whatever. Doesn't matter. We got exclusive access, the only thread that locks it that have access to it, which is nice. Okay, and the other threads that tries to lock the same data so we can have access to it, they're just gonna block. And in the case of a simple like the standard library mutex, it's gonna block the whole thread, like basically all the tasks that are in the thread. So, which is fine as long as you don't have a lot of contention between the threads, which means basically like all the threads, a lot of threads are fighting at the same time for the lock. Sometimes it could be fine to block the whole thread. But anyways, there's a lot of things that I'd like to not go into details right now. And RAW lock. So RAW lock is very similar to mutex, though it have some interesting feature. So the thing is, why we need the mutex, why we need to synchronize, what is the problem? The problem is when someone is writing, like some thread is writing, and some other thread tries to also write or even read. Because if it tries to write, then well, they could have like the thread 1 could write something and thread 2 could overwrite that something, or maybe even it could happen so that thread 1 have written some data there and thread 2 have written some other data. Like you can have some mixed up data which basically is corrupted or something like that. The other case would be is that one thread is writing and another thread is trying to read that data at the same time, which means the thread that is reading can get incomplete data, or so basically corrupted data. So we could use a mutex, but the problem with the mutex here is that it doesn't just block the writers, like it also blocks the readers. So the thing is, if we have just multiple threads reading at the same time, it doesn't matter. Like we don't really need any synchronization, right? We don't really need to lock anything. And that's where RW lock shines, because while mutex, even readers would get exclusive access and would need to lock. In RW lock, no. For readers, they don't have to lock, right? So RW lock only locks when there's a writer. If there is a writer, then that writer would get exclusive access, which would kind of serves like a mutex at that point. But though RW lock is a little bit more complex, so it's probably a little bit less performance than mutex. And also there's the other thing is that a mutex can have a value that is not sync, I think, or something like that. And RW lock could have a value, should have a value that is sync or something. I don't really remember exactly what is the specifics, but anyways, that's all you need to know for now. So in this case, we want to be able to like read the client names hash map from multiple threads, fine. But like when we have a new connection and that connection or that client have, you know, typed the name that he wants to assign to himself, right? And then we want to insert it into the client map names hash map. Then at that point, we want to lock the access to the hash map so no readers can access or any other writers cannot access. So yeah, now let's get a lock here. But before that, of course, we gotta use arc. So here we're gonna use RW lock. And most of the time, honestly, I would recommend using RW lock as a default, because most of the times you want to not lock like the readers and to only lock when there is a writer. So RW lock, like instead of mutex. Anyways, let's say RW lock new hash map. Import. And here we have SCD sync or Tokio sync. Now the default would be SCD sync, but there is some other cases where you may want to use Tokio, but most of the time you just want to restructure your program or use something else. But anyways, let's just go for now. It's fine with SCD sync. I'm gonna explain later why you may need the other one for from Tokyo. But anyways, so here now we got arc rwlog of a hash map. Great. So now what? Now here we have another error at this point. No method insert found for struct arc rwlog hash map in the card scope. Let's go. Why? Because, well, we have to lock, since here we're trying to write to it. So we have to first of all get a lock to it. We want to not allow anyone else to get access to this data at this point. We want exclusive access. So let's lock it as a writer. So client names writer, let's say. You could call it, of course, whatever you want. Let's say client names dot write. Right here we get lock results and lock result. Now here this actually gives us back a lock result, and it would basically be okay, of course, if everything have gone okay, and it would give actually an error if the other thread that had the lock was poisoned. And what poisoned means, like if the other thread have panicked, for example, or something went wrong with it. So the data could possibly corrupted. So basically this function will return an error if the rwlog is poisoned, and rwlog is poisoned whenever a writer panics. So writer panics while holding an exclusive lock. An error will be returned when the lock is acquired. So here let's just unwrap. So if something happens wrong, we're also gonna panic. So yeah, you could choose to ignore it, but then you have to be prepared to handle any kind of weird behavior in that data. Anyways, rwlog write guard. Now we could actually use our client names writer instead to insert stuff, but we have a problem. Use of moved value. Cannot borrow as mutable. Okay, let's actually make this mutable, because this have to be mutable since we're gonna write to it first. Now let's actually build this, and there you go. We got another error. Client input does not live long enough. Client input. Now I think the first problem that we have here is that yes, we got an arc. While we indeed got an arc, but we cannot like send this arc to all the threads just like that. We have to like again clone an arc like a handle so we could share like access or ownership actually. So let's client names, let's say let's just say that, and let's say client names dot clone, and then this Tokyo spawn would actually move it in. Great. Future cannot be sent between threads safely. Okay, great. Now we have another problem for some reason. Let's actually unwrap this. Client input does not live long enough. Where is client input? Here. Well, here we're actually cloning it, so we're getting the string now. Yeah, there you go. Okay, so yeah, clone was doing the wrong thing. Okay, there you go. So that was the problem. And what else? Future cannot be sent between threads safely. What does that mean? Oh yeah. We got here an rwlog, so we gotta make sure to unlock it after that. And to unlock it, there's two ways. You could either, it's an RAI guard, so you could either, make it into its own block essentially. Of course, just while you need it, try to keep the block, like the scope, as small as possible, so other threads could actually take hold of the lock and do whatever they want with it if they want to. So here, client names writer dot insert, client socket addr, client input trim, toString. Great. So here we're just trimming, removing any spaces or new lines that are in, in the margins. And then we're turning it into an actual own string, so we could send it, we could store it in the client names writer hash map. Anyways, so yeah, that's basically it. Otherwise, if you don't want to do this, you could just say drop client names writer, and this would drop the guard to, which would be fine, but currently I don't think the compiler actually handles this very well, because it doesn't really understand that you're dropping it here, kind of. So yeah, honestly, either way, I do recommend going with the creating a new scope like this. Even makes it very explicit what's going on here. So that's very nice. Amazing. So this should do the trick. Now for inserting, like when a new connection connects, it can actually insert the client name. Great. Now how we can actually get the client name? Well, we actually need the client name here. So instead of message client socket address, we want to get the name. Well, how we could do this? Just say let. Now, honestly, we don't even need to send. Oh well, actually, we do need to send the message client socket ADDR because we're gonna use it as a key, right? So let's say let client name is equal to. But first of all, we need to get a lock, a reader. Not a lock, but yeah. Anyway, let's see, read lock. So let client names reader is equal to, well, client names dot reader, or read basically. We could also use try read if we don't want to block when someone else got the lock, but here this would just block if someone else got it. So anyways. So here client names dot read, and if someone is poisoned, we're just gonna unwrap. And what else? Yeah, right now we got the lock. So what's next? Right now we could actually use the hash map to read from it, not to mutate, of course, because we didn't get exclusive access, we just get read access. So here get, and here we could use the key. So message client socket ADDR. And of course it takes a reference actually, and there you go. And this would actually give us an option. Well, we know for sure that this client would have a client name, since otherwise, like, this is the first thing that happens. Okay, we are making sure that that's the case, so that's fine. As long as we got a message from it, that's for sure it's gonna have a name. So yeah. Now what's next? Now we got basically a string, a reference to a string, which is cool. So what we could actually do, because I don't want the lock anymore after I get the name, I could just probably say client name is equal to this, basically. So we just get the read lock and immediately just get what we want and, drop the lock at this point. Great. So now after this, we can, instead of using that one, we could do this. Though here temporary value block, temporary value dropped was borrowed. So this wouldn't allow us because this would borrow, we'd want to borrow. So what we could do here, we could just make this into a block. And we could call this, I guess, client names reader. And then we could just return from the block client names reader. Dot get and stuff like that. And of course we don't want the semicolon here because we want to return back the actual thing into the client name. The problem though with this is that client names reader does not live long enough, and which is actually true, because once you got, like, the lock gets dropped, you don't have access, the reference doesn't live anymore for the string. So we cannot do this unless of course we have cloned it. Now here actually depends if you like want to, well, actually honestly that's a bad idea, right? Yeah, that's a bad idea. So let's just keep the lock. Let's just keep the lock until we're done with it first. So we're just gonna say this honestly. Yeah, fine. And then client name is this. We don't want to clone. Alright, so and here once we got a formatted message, we don't actually need that anymore. So here where we could, like, let's say do something like this, let formatted message. I mean, this is fine, but well, we're gonna be waiting for write all, then you're gonna release the lock. So you'd better as much as possible release the lock as close as soon as possible, so other threads can actually get hold of the lock if needed. In this case, if there is some writer that wants to write the client name, they could get it at that point. And here what's happening, well, yeah, I'm just gonna return the formatted message, and this would allow us to do that because at this point we're just getting a new string and we're not like having a reference or something like that. So that's pretty cool. Lovely. And now this should do the trick, I think. Yeah, I forgot a semicolon here. And let's try now. Let's try now. Let's get our beautiful things here ready. And the thing is here, gonna say, let's call ourselves something. Go to Taku. Oops. We got a problem. What is the problem? Let's see. We got it in the writer for some reason. That's interesting. Tokyo runtime work panicked. Oh yeah, my bad. My bad. So this insert actually doesn't return like it returns an option, and it basically returns so if the map did not have this key present, none is returned. So if there is another value already present in that key, it would just give it back to you. So honestly, we don't really care if there's, actually we do care. We want to make sure that the client have a unique name. But anyway, for now, it's fine. Who cares? So it's fine if they have like the same name, though not ideal. But anyway, for now, this is, we're just gonna ignore if there's any value there. So yeah. All right, great. So let's see. Okay. Well, that was scary. Let's say Coda Taco here. Let me zoom in a bit. So here I've told it that my name is Coda Taco. And let's say here, I don't know. Let's use my real name here. Yes. And there you go. Right now, I think at this point, we have got names ready. Now let's say hello. And notice right now we're getting Coda Taco hello world. And if we use this client, we can say how is it going? And there you go. Right now we're actually using the names themselves. Let's go. Nice. Lovely. Great. Great, great, great. Though we could indeed use our names here instead of yeah, we could write the names and then like the user could just continue with the message, I think. Yeah, maybe. But there you go. Right now we have that on, so that's nice. Now the thing is that I wanted to show you, right, is that if we have the two clients and if they choose the same name, for example, Coda Taco, depends. I mean, if you're fine with align this in your server, it's fine. Nothing is here. Like hello, world. So both would have the same name, which is going to be confusing. So let's not allow that. Let's not allow that. Okay, so how we can do that? Let's see. Basically, and the thing is, we want to check if the key, like if the actual value is already present in the hash map. Now that's quite interesting actually. Because if you want to do that, we have to go with like some sort of linear search through all the entries trying to find the value. Otherwise, we could go with a second hash map that would like store the reverse. So you would go from a key, which is the name of the client, to the actual socket address. So it depends, like, do you want O1 to access the socket from the name, I guess? Or like we could have some set even, possibly. Yeah, we could also have a set instead. So yeah, which one I would like to go with? I guess for now maybe let's keep it simple and let's just do a linear search, I think, for now. So let's go with, for I guess, entry maybe, or let's just say actually self dot. Well, here I'd like to get read access essentially. Well, honestly, let's just do it after maybe getting the right. No, I don't want to do that. Let's just get a read access for now. So let client names reader. I don't want to block others while seeing if the name exists or not. So let's just say client names to read. Though we're going to be blocking the writers as a reader, so that's just something to keep in mind. But at least we're not blocking the other readers. Anyways, so client, read, and wrap. Now let's go through all the keys. Well, let's see. And let's try to find that specific client names. And actually, let's grab the key here. So client name, right? So this is the client name that we want. Like client name is equal to this. And also after that, we could clear the thing. That's why not. Okay, great. So now what? Client names, I guess dot keys, or like actually dot values, but yeah, or in wrap. Yo, what's happening here? Interesting. Why can't I access anything here? Read guard. Watch. Weird. Did I miss something here? Interesting. Client names. Okay, there you go. So I was using the wrong thing. Okay, interesting. So now let's say it contains, no, there's no contains value, which is good, since basically the API is not allowing you to do that easily, because, well, it's linear search. So anyways, let's see. So now I guess we gotta take the values. Get key value, huh? Here you give it the key and it gives you both. Interesting. Otherwise we could just say values. Okay, so let's go with values and let's try to find this key. So find key, and we're just gonna see if the key is yes, EQ. I'm not sure if Rust strings equality checks for the contents. Probably yeah, but yeah. So let's say client name, I guess. Now let's actually remove one reference, I think. Expected string. Actually, just to go the other way around, really. Say, I guess, client name dot EQ key. There you go. Did I really need this? Yeah. Great. Great. And I don't think EQ, yeah, it just takes a reference. Nice. So now, if we find something, then, well, we want to ask basically the reader to get some other string, some other client name at that point. So in wrap, in wrap. So how are you going to do this? Well, so this gives us an option, right? Find. I think, yeah, probably an option. There you go. Okay, great. So now, if is sum or is none, we could say, then I'm gonna honestly break of what? Because I'm gonna have an outer loop. I'm basically gonna be constantly asking the client for a new name if like the name already exists. So I'm gonna loop through this essentially. And there you go. So loop, and here we're getting a new line from the user, and framing the client name, and notice here where we get the read lock. So if we fail, we just release the read lock first, then we wait for the read line, then here we get the read lock again and stuff like that. So we don't lock, we don't want to lock this here, otherwise it would just like keep on locked, like no client can actually submit the name while this is happening, so which is bad. So client names reader, client names read in wrap, values find key. So if it's none, which means that the key is available, we can break out of the loop, I think. Yes. And this is actually not key, but the value, because we're going through the value actually. So client name EQ value, there you go. Then break. Otherwise, it's gonna loop again. You know, keep on going. And in fact, before we, after this, if we don't break, I'm just gonna tell the user to retype again. The name is taken. So stream. Well, actually not really here. So after releasing the lock, we can tell the user so. So stream writer, I think, yes. Well, honestly, we could also wrap the writer in its own buff writer too for efficiency. Because right now I think we're probably writing one by one, though I'm not sure. Yeah, probably. But anyway, for now, let's just say write all to the stream writer, and we're just gonna say the name is taken. Please choose another name. And there you go. And what's now? Expected by found. Right, let's make this into bytes. Or let's say please try again with another name, I guess. Yes, and in wrap. When this fails, by the way, that writes returns. Okay. Anyways. So now what? Now what? And of course, before we really even ask the user, we could just like ask him for the name, essentially. So stream writer write all. Yes, stream writer write all, and let's just say name, basically. Dot await dot in wrap. Of course, as bytes. Great. Now I think maybe let's try this. Yeah, here we're asking every time for the user to type a name, and then let me make sure to add a new line here. Actually, I think there you go. And yeah, but then here we need the client name. Yeah, the client name should not be here actually. The client, yeah, the client name should be here. Yes. We may want to limit the name, of course, of the client, indeed. But yeah. And then we're just gonna mutate the client now at this point. Great. To string. Yes, client input. Oh. Okay, hold on a second. No, hold on a second. Let's remove this for a second. I want to think this a bit, because right here I don't. Yeah, we could just trim the client input and probably just try it directly. Actually, maybe. Yeah, probably. In fact, and. Yeah, seems like. But of course we gotta make sure to clear this guy after the fact. After we're done with the name completely. So here we could just say client input trim dot as bytes dot toString, of course. Oops. Huh. Interesting. No. toString actually. And there you go. Great. Lovely. And here, why I've done this way, because here when I just want to check if the name is taken or available, I don't really allocate any memory here. Notice I'm just trimming, which just gives me a slice over the existing client input string, and I just check that if it's equal to the value. Then like that is already like, yeah, in the values, right? So yeah, basically I think right now we're good to go. I think right now we're good to go. And then yeah, let's just see how this now goes. Okay, say telnet, and notice it asks me for the name. Go to taco, and there you go, I'm in. Here, if I ask for the same name, go to taco, the name is taken. Please try again with another name. If I try again with the same name, of course, ooh, why? Interesting. It just blocked. Actually, it just let me in. Huh. Well, that's interesting. Why that's the case? So values, find value. So if it's none, then break. Interesting. Yeah, Rust check if string equal, just to make sure. Not really what I want. And they seem to be using equal equal. That's interesting, because the thing is, while it's taken, you know, it's just gotta actually repeat this loop. I mean, indeed, at that point, it said name is taken. Great. But why it didn't loop back? That is actually quite interesting. Or maybe it did, but something funny happened. I'm not entirely sure. That's weird. Yeah, I'm probably doing something wrong. Because indeed it did say the name is taken. Please try again another name. But after that, I'm not sure what really happened there. Well, that's interesting. Indeed, super interesting. Great. Though I gotta be careful of something actually. No, I guess I dropped the receiver here. Is it? Actually, not sure if it really drops the receiver like this. It should be, because otherwise it's gonna be sent into this receiver until, you know, it's like it exhausts the memory. Interesting. Yeah, there's a lot of weird like stuff that could be exploited here. But anyways, kind of like just memory leaks waiting to happen. So yeah, go to taco. That's interesting. Okay, actually it asked me again. The name is taken. But yeah, I guess when I have actually done it, right. I gotcha. I see. That's the problem. Basically, I didn't clear the client name after it failed, right? So So before we break, hold on. Actually, if client names is none, here basically we're breaking up the loop, which means that the name is available. But else, if it's not available, then we want to clear the client name. So clear. So when the client gives back another name, we wouldn't just accumulate. So yeah, that's why that happened that way. Interesting. Alrighty, that's first thing. Great. Let's create this. Now, as you can see, both here and here, could actually give it a name. Let's say here Kodotaku, and there you go. Great. Let's say hello, but of course this one is not connected. I'm not gonna not receiving just yet. So now let's say name. Let's try Kodotaku. Let's try again Kodotaku. As you can see, it's gonna keep like this. Though we could have some sort of a limit of how much you can retry, so we don't get DDoS, I guess. But anyways, whatever. Because the thing is, if this keeps on happening, then we're gonna keep on getting read access, which would fight over with writers, which would kind of slow down clients that wants to actually have write access, so they can write the name to the hash map. But anyways, whatever. So let's just try something else. And right now I got connected, and as you can see, I indeed got my message from Kodotaku here. The message that been sent here. Because the thing is, we start actually getting messages. The moment we connect, we start getting messages. So that's why this hello, actually we got it here, which is interesting. So yeah, yep. And that's pretty much it. The other thing that I'd like to add is when you write something, your name also happens to be here. So let's go with that, I guess. I'd like to also possibly add some colors. That would be nice. And yeah, pretty much. Great. Can't believe we have made this. Let's go. But what else? Yeah, I wanted win read a line. Send client input clear. Okay, so loop. So yeah, in the loop here, here we're gonna ask. Actually, that wouldn't be good, because actually that would be good. Because when we got a new message, ooh, that's gonna be interesting. Yeah, no. Because when we got a new message, it would be, yeah. Let's just let's just ignore this for now. I see some problem there. Not really a big problem in terms of something, but yeah, whatever. So basically, if we write Kodotaku and then we receive some new message, then yeah, what happens then? You gotta somehow clear the Kodotaku that we have wrote, or the input of the user that we have wrote, and then write it again somehow. I'm not sure how to do this actually. Maybe something using cross term or whatever, some actual client that we program ourselves. But anyways, whatever, I don't know. What else now? Yeah, let's try to add some colors. I'm not sure how we can add some colors here. Well, let's see. Rust. Text color, I guess, or something. How do I print? So you can use the color to crate. Yeah, I remember there's a color crate and there's colorized crate or something like that. don't remember what's kind of the difference between them actually. I'd basically like to color some things, like for example the name of the user and stuff like that. So here we could also possibly add the date at which the message have been sent, stuff like that, whatever. So how are we gonna do this? Yeah, let's look for the colored crate. The most simple way to add the colors in your terminal, updated 4 months ago. Okay, what about colorized 11 months ago? Yeah, let's go to colored probably. There you go, coloring terminal, so simple, I already know how to do it. Interesting. Cyan. Great. Now let's add color to our dependencies. So, okay, cargo add colored. Kind of paranoia about the stream. From time to time I check out on the stream, making sure my mic is on and everything is alright, so it seems good. Anyways, so we have added the colored crate. Now where we're actually, here we go, the client name. Okay, so here in the client name I want to basically color it. But before we could color, I probably need some trait, so some extension trait, right? So we could, like, you could add this green and stuff like that to our strings. So here, extern crate colored, we don't need this. And here, use colored, okay. So let's add this. And in fact, we don't need this currently, though we're probably gonna need it later on when we buffer the reads from the stream or something like that, whatever. So we'll see anyways. So colored here, but if we need it we could just add it anyways. Let's just say this. Now we got the colored crate. Now we could actually color stuff in. For example this, the name is taken, please try again with another name. And we could try to say red maybe. There you go. Does this allocate? I think so. Yeah, it does allocate, but it's fine. Who cares? So this would be red, basically, like an error, essentially. Yes. And what else? So that's gonna be red, and this one. Well, this one would be, let's say, I don't know, maybe yellow, possibly. Great. And here, client name. Let's say dot yellow, maybe. Or actually, let's say no. Let's say something like I don't know, cyan. I'm so bad at colors. And then the message, or let's say blue. Let's say blue. Actually, blue wouldn't be so. Maybe bright blue, yeah. And message, let's say maybe cyan, just so it's distinct from the input color, I guess. I'm not sure. We'll see. We'll see how it goes. How it looks. That would be nice. Yes. Let's see. Oops. Damn. Let's connect. Ooh. Maybe Telnet doesn't support colors. Possibly. I called myself hello. Oh, okay, so that actually works. But the yellow color, I believe, didn't. Interesting. Let's see. Let's make sure we're doing this. Name. Yeah, I'm setting it to yellow, but it doesn't work out. So I guess it doesn't work on my own thing. So let's try some other color, I guess. Let's call this green or bright green. Rich, what else? I think that's it. Rich. Yes. Oops. There you go. It's still, the name is not being written in the correct color for some reason. Weird. Maybe because it's the same in the same line as the cursor. Possibly. Yeah, possible. So maybe if we say name and then like give it like a new I mean, let's try that out actually. Like, yeah, correct, let's try that out. And let's see, now I just basically enter in a new line essentially. So yeah, ooh, still like that, weird. Maybe bright green is also not available, possibly. So let's just try something that we know that works in actually. So what worked? Bright blue, I think. So let's go with that, I guess. So at least for my own terminal, I'm not sure what our terminal is basically. And it probably also depends on the clients. So in this case, telnet, and it still doesn't work. Weird. Yeah, maybe I'm doing something wrong here. I have no idea. Weird. Let's try again. Right now, oh, okay, no. I have no idea why this doesn't really work. Honestly. Interesting. Like, why the others work but this one doesn't? Maybe we need format. No clue. No clue, honestly. So yeah, fine, just say name regularly, like fine, whatever. And yeah, whichever. So right now we got some colors at least. Amazing. And this is client 1. This is client 2. Hello, world. How is it going? There you go. Nice. Nice, nice, nice. Let's go. All right, what else? Yeah, I want to give one remark about the hash map thing that we're doing here. Arc new, RW log new, hash map new. Now, the thing is about this. Let's say you're gonna have a lot of keys here, right? And like a lot of contention basically. Let's say a lot of threads are fighting over this hash map, over this RW log actually. So how can you solve that? Well, there's a lot of ways, a lot of ways. But the thing is, there's a simple way which is called charted. Yeah, basically charted whatever. In this case, charted hash map. Yeah, right. So, and charted basically, instead of having one hash map, you would like have a vector of RW log of hash map, and then you would like hash the key, and then try to find the key in which, like from the hash, you would determine on which hash map and which RW log you would read and stuff like that. So basically, you're kind of like distributing the kind of contention over multiple RW logs essentially, and over multiple hash maps. And that's what's called charted map. Now to implement that, it's actually not that hard, but honestly it's gonna take some time. So honestly, I would really recommend not doing it yourself anyways. Like even simple RWLog, I don't recommend that you do it yourself. I do recommend though using some library, like for example dash map. At least these are seems like the most popular. It's called a dash map, and this is basically what I've described: a charted hash map. So, and even hash set, it even gives you a hash set and this other stuff, which I'm not sure what is there about. Read only view. Interesting, shared value. Anyways, whatever. Let's go to dash map, so we're interested in here. And yeah, you could read all sorts of cool things. And here you could actually give it chart amount, like how much RW logs and hash maps you want. In this case, we only have one chart. Basically, we don't have charted hash map. We're just gonna have one chart. But you really don't want that. Usually, like most of the time, you want to have multiple charts. So yeah, now let me show you just the implementation real quick. Like if I go to source here, yeah, there you go. So the dash map, it just takes three generics: K, which is the type of the key, V is the type of the value, and S is the type of the hasher. By default, it's a random state, just like how this is basically like hash map. It also takes these three keys, and S is by default just a random state. And here, this is basically the default hasher essentially. And now here we got this shift, which does which is involved in like the hash for which to select the chart essentially and stuff like that. Anyways, as you can see here, charts is a box of RWLog hash map KVS hasher S. So box, I mean, this could be just a vec, right? But box is more optimized in this case, since you don't have to store the other stuff about the vector, like the length and the capacity. So yeah, and here we got RWLog hash map, so like a array essentially. Well, not an array, but basically this is like an allocation essentially. Like in the heap, we're gonna store this kind of array thing, or like slice, whatever you want to call it. Anyways, not really slice. Anyways, so here, so basically heap allocation, which contains a collection of these values. Here we got the hasher, of course, and yeah, so you could just read through this and see how it works. But anyway, for now, I'm not gonna use these, though we're still gonna need arc, of course. We're just not gonna need this RWLog hash map and box or vec or whatever for charts, etc., etc. And it's more robust and performance possibly. So instead of rolling our own concurrent hash map, we're just gonna use dash map here. Cargo add dash map. There's some features that you may be interested into, like rayon for parallel, for parallel iterators or something like that. But anyways, so here RWLog new hash map. Okay, great. So instead of this, of course, we're gonna leave the arc for shared ownership. And here, just gonna, instead of doing that, we're gonna say add dash map new. That's as simple as that. If you want to control the chart or something like that yourself, then you could say with chart or with capacity, etc., etc. But honestly, for now, I don't care. Let's say new. And this should probably behave almost, if not the same. Yeah, almost the same, I guess. Let's go. Okay. So let's see what we got here. So probably we don't need to lock it ourselves this time. Okay, probably we could just go directly and say client names.values maybe. Doesn't seem like interesting. It doesn't have the values for some reason. Yeah, that's interesting. But like, how can I get the values though? Yeah, how can I get the values? I guess I should go with int trace or something. Yeah, how can I iterate over this? This doesn't make sense. Let's try iterate over this. No need for values anymore. And this gives us some sort of ref multi. Oh yeah, okay. So this is like the entry essentially. Entry.value. And there you go. Okay. So just gotta change the interface a bit. Though ideally you should have had such a function called values or something like that. But anyway, whatever. It's fine. What else? Do we have to change anything for this to work? We don't need a hash map anymore. We don't need to roll our own RW lock anymore, for that one at least. What else? Is there anything else? Type annotation is needed. Okay. Can't it just know itself? But otherwise, actually, hold on a second. So notice that we don't need to lock ourselves. Basically, when you're gonna be, I think, iterating or something like, yeah, iterating, you're just gonna hold the lock while you're iterating, I think, while the iterator is, alive. So here, locking behavior, as you can see, made it lock if called when holding a mutable reference into the map. And yeah, before I wanted to explain something, which is the fact that like you shouldn't await something while you're holding a lock, because once you await, as I said, you give the opportunity to the executor, which is Tokio in this case, to execute some other tasks, right? And those other tasks may want to actually hold the lock. And if you're holding the lock and then you await, so you run another task, then that means that task that Tokio have run would actually block, which means you will have a deadlock where like no one, because both are like waiting on, like that one is waiting on the lock, but the other one to release back control to Tokio so it would run the other task, it needs to release the lock. So you have a deadlock basically in your application, and yeah, the application will just hang essentially. And that's the first thing. Second thing on the same note is that when you await, yes, you give control back to the Tokio runtime, and at some point Tokio gives you back control into the await, so you can, like, once the operation is done for that await, and at that point it's not necessarily going to run in the same thread or like the same task. Not necessarily, like it could run on a different thread or a different task. Like it could resume after the await on a different thread or different task, and at that point when you're going to resume, you're not going to have the lock if you're another thread, right? So you're screwed at that point. But anyways, and in fact Rust would probably not allow you to do that anyways, I think, because it's centrate and stuff like that. But anyway, whatever. And if you want to solve that, probably the best way is to just restructure your program or use some other primitive. Though if you really need to await, like to lock and await at the same time and go back and still have to lock in the task after the await, you can use Tokio mutex instead of SCD mutex. But that's just a side note. Alright, just so you need to make sure you don't lock and then await or something like that. So, and in fact, as I said, once you lock, you need to as close as possible to release the lock. So other threads and other tasks could actually use it. Anyway, what's happening here actually? Client names, clone. So it needs types, but why didn't infer the types now? Fine, let's just go give it the types then. Okay. So in our case it would be Well, it's gonna be socket addr value. Yeah, we have a, if I remember, there was like a string for the message. I think that's it. No? Yeah, actually for the name, right? So yeah, I think so. There you go, client names. Okay. Yeah, I think the interface changes here too. So you probably don't need to lock anymore here too. Just say client names directly. Don't insert, I guess. Yes. Because in fact you can't even lock like that, like the data structure itself like holds numerous locks, you know, and it just does the locking for you. So yeah, interesting. The one is gonna release the lock here, I guess, after the insert is done, right? So that's nice. What else? Here, same thing. So we don't need to lock anymore. Just gonna directly get the client name. And yeah, and as you can see, even the code is much simpler because we don't have to like create like hold the locks ourselves and release them, etc. But anyways, and we could also resize the chars easily and capacity, whatever. Cannot move out of a shared reference. Well, that's interesting. What shared reference? Oops. Okay. And I guess that's all we really need. Right now we're using a dash map instead of our own crappy solution, I guess. Okay. So right now it should be the exact same thing, but right now we're using dash map instead of our built like home solution. Let's see. Kodotaku, Theo, hello world. Hey everyone. And there you go. So that's essentially it for that one. So what we should add, I believe right now we got this reasonably complete chat, though of course it doesn't account for some things. And honestly, I don't know, by the way, if when you do this, would it really... So just to make sure I don't have any kind of, you know, surprises, honestly, I'm just gonna drop the receiver here explicitly, just to make sure it's really dropping it. Because otherwise it would just keep on, you know, getting the messages, queuing the messages, and no one is actually consuming them, which of course wouldn't be good. In fact, I think it would possibly block at 32 messages. Yeah, maybe. But right now that shouldn't happen, I think. Yeah, I think so. Great. Really good. Nice. Great. And there's some other things, like for example the client name. Maybe you can make sure that it's, I guess, that is less than some length, like let's say less than, I don't know, 16 characters or 32. So for example, like we could say, and also another thing that I wanted to say is the fact that you should be careful about, you know, doing stuff on the stack, like arrays, for example, big arrays or something like that. Why? Just simply because in async, Yeah, I gotta actually explain a lot more. But basically in async, these things that are in the stack are actually stored in an enum. Like all these features are in an enum and stuff. But yeah, basically, I don't want to go into details here, but basically be careful about storing a lot, like big data in the stack. But I think like a little string wouldn't be a problem, I guess. But we're using the client input later on for the messages anyway, so who cares, fine. And the only thing here that I would honestly make sure, read line, huh? Client names that are fine. Okay. Here we're gonna break, and we can make sure that the client input dot trim dot len is less than some max name length. So you could say const max client name length, use size, or let's say 32, because I think that's a pretty reasonable name. If not even 16 actually. Honestly, I think probably 16 is fine. And even because of this assumption, we could possibly optimize some things, maybe. But anyway, whatever, let's keep this simple. So is none, and is less than max client name less, then oh yeah, I don't need actually this anymore because we don't have a lock there anymore. Now here it depends. It could be that the name is taken or that the name is too long. Interesting. So honestly, let's keep this separate here. I think. Not sure. Let's see if well, honestly, instead of doing this, like, yeah, we could just say stream writer, honestly, like this. And in fact, let's check the name length first. Why? Because, well, that's much less expensive than checking all the client names. So let's go with that first. So if it's less than the length, then we could basically break. Well, else, of course, we're gonna make sure to always clear the input. Actually, we could probably just yeah, let's say continue here. Although actually we don't need it here. Yeah. So I'll say here client input to clear. Then we could continue to the like. What happened here? Unreachable code. What? Oh, because this would break. Otherwise, it would continue. That's interesting, actually. Well, we don't want to break, actually. Yeah, we don't want to break. So greater than or equal to. We're just gonna say this. Actually, we don't want to clear either right now. We're just gonna continue. How that would work, actually. If it's greater than maximum client, we're gonna tell the user that it's too long. The name is too long. Please try again with the shorter name. Right. And what else? Continue. So it's greater than. Max. And then we're just going to continue to the next stage. We don't want to check like if the client name, because we know that this is invalid anyway. So why bother checking if it's already taken or not? Else. So we're gonna let the user first of all, make sure that the name is short. And yeah, that's pretty cool. Else. So what if it is? Yeah, I don't think we're gonna do anything here. Yeah, I don't think it's fine. I think so. We gotta try these actually. So let's try these. So we got launch the server now, connect using telnet, and let's see. So the name, let's say go to taco. The name here. There. Oh, oops. Let's actually control that guy so we could disconnect. Let's connect again. Let's try to use Coder Taco here. As you can see, the name is taken. Please try again with another name. And I'm not sure why sometimes the colors work and sometimes it doesn't. Maybe Telnet has something to say about that. Anyways, the name is taken. Please try again with another name. Great. Amazing. Now let's try some big name. Let's say, I don't know. 1, 2, 3, or let's just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The name is too long. Please try again with your name. Nice. Code. Hello. Ooh. Interesting. Why don't receive? Yo, which? Why? Oh my god, why this broke? Weird. Could have taco. Why it works now? That's weird. Why it didn't work before? honestly, by the way, I'm probably gonna wrap the stream writer in its own kind of buff writer. Yeah. That may be the problem actually with colors, possibly. Maybe we're like writing byte by byte or something like that. And then it breaks telnet or some sort of thing like that. No idea. Yeah, but we need to figure out first, like, what is going wrong with this first. Like, it's greater than max client name length, and we basically clear the client input. And honestly, instead of having to worry about clearing the client input, really, let's just clear every time I want to take input from the user. That's much cleaner. Great. But anyway, fine. Let's not worry about that too much right now. And now, yeah, I'd like to create some buff reader here. The buff writer, sorry. Writer. Just to make sure we buffer writes into the stream instead of sending byte by byte or something like that. And here we're probably gonna need the trait. Maybe? Probably. Actually, I already have it now. No, I don't. Maybe I need write.txt. Oh, that's interesting. Yeah, why there's only buff.txt? Okay, so the trait bound right half is nonsense. Oh, hold on a second. There you go. Yeah, I knew that was the problem. We're using std. I see. Makes sense. Let's make sure to use Tokyo one. I guess that should be good now. Not sure if I need mutable. We'll see. Great. Now I got the buff writer. Now instead of using the stream writer, which it's already complaining because this takes control of it, like takes ownership of it. Yes, should be mutable. Here you go. Rust analyzer now. Like the Rust borrow checker is helping me here. This is not an error, it's just helping me. Okay, great. That's what I love about Rust too, is that it's pretty easy to refactor stuff without blowing everything up. So yeah. Yes, I see. Okay, let's try now. And is there anyone who wants to test this with me? Let's see. Oh, why it's not? Ah, I know. I know. Now we're gonna make sure to flush the stream when we want to the message to read, like reach, to be sent essentially. So for example, here stream buff writer, we want to immediately flush it. So this would make sure to send the data that we have buffered until now, because we do need it now, so makes sense. Ooh, now I'm gonna make sure to flush every time. Not sure if we really need that, honestly, at this point. Like write all, does it like write by byte? I'm honestly not entirely sure. Hmm. Well, that is interesting. Here's the poll. Not really sure. Yeah, no idea. But I guess it's fine. Just gonna make sure to write all. Every time I write all, I gotta flush when I really need to flush, essentially. Yes. Same thing here when we send the message. Bruh. Why this doesn't auto format? What? Weird. But anyway, so now this should work actually. As expected, let's see. There you go, right now I got name. And we still, well, let's just say code boot check. Let's connect here. Hello, the Vrisco. Welcome to the live stream. How's it going? And you have come in the right time. Can you test this with me? Using Telnet as a client. Name. Amazing. So it works. Great. Now if I actually disconnect, like let's see if I disconnect. I connect again maybe. Ooh, I forgot when you disconnect I need to remove the name. That's interesting. Yeah. Yeah, we're not keeping track of connections currently, but anyways, whatever. So name here we could say, I don't know, Kodo. Yeah, interesting. Something is weird with disconnecting. Yes. But anyway, I'm gonna send you the public IP and the port. And actually I need to open the port first, so hold on a second. Gonna open the port and then you guys can connect with me. We're using Telnet. Let's see. Or whichever client, you know, that can connect. Doesn't need to be Telnet. Whichever text client, TCP text client. So let's see. Let me open up a port. Rich port forwarding basically. Let's see. I never remembered the password. Let's see. Hold on a second. Okay. Okay, there you go. I'm in. Nice. And let me go to, okay, so I'm in the, I connected using my gateway. So 192 points or dot 168.1.1. This is my gateway. And it probably would be the same for you, maybe 0.01 or something like that, but yeah, it depends. And in my router, at least, you go to, I'm not local. Hold on a second. Trying to remember. Oh yeah. So in my router, at least, I go to a tab called Internet. Then I go to Security tab, and I have a lot of options there. Like anti-DOS attack and firewall, blah blah blah. But there's also another sub-tab called Port Forward, along all sorts of weird stuff like DMZ, ELG, blah blah blah. And yeah, I'm not sure if I can show you this. Let me make sure there's no weird data here that shouldn't be visible. Let's see if I can show you this. Also, I'm just going to give you a capture of the data that I'm going to fill in here real quick. Well, let's see. So here, yeah, I'm just going to make this on. I've already have port forwarding on, and the port. Let's just play it safe. I'm going to go with this port actually. It's a big port. Okay, great. And localhost should be fine, maybe. We'll see. Anyways, so this is it. Let's apply. It doesn't have to be UDP. Let's just go with TCP because we're only using TCP. Right. That's basically it, I think. And of course I have a fixed local IP, so that shouldn't be a problem either. Not public IP, of course my public IP changes, so that doesn't matter. I could give you my public IP without any problem. Right, let's see. Basically this is kind of like, let me give you a capture here of the configuration, for example, in my router, though of course this would change depending on your router. Oops, this is very low quality, but anyway, so I have port forwarding here. I can create new items here. I have this item here on for now, though of course when you're done with it, just make it off just to make sure, you never know. Protocol here, TCP, and the name just arbitrary, whatever. WAN connection, the auto, whatever. Host IP address, whatever. LAN host, this is my own local IP in my network, and honestly fixed it so I don't have to constantly change it every time whenever I want to port forward. So static, and then not the public IP, I mean the local IP of my computer. This is basically, and then there's the WAN port 30,000 in this case. Doesn't matter again. Of course, it's just gonna be the port that you're gonna do. It's gonna be safe port 2. Anyways, here LAN host port, same thing. So just this is the range, the port range and stuff like that. Just apply, and there you go. Right now, the actual port is open. So now I'm just gonna give you my public IP, and let's see. so you could just search what is my public IP, like any website that you actually like visit, it's gonna take your, it can get your public IP as long as you're not using a VPN. But then when you're using a VPN, the VPN, like the VPN server that you're connected to, is the one that actually knows your public IP at that point. But anyway, this is my public IP. Let me copy it to you. Let me launch a server here. And in fact, I'd like first of all to notify myself when some server, when some client gets connected. So how can I do that? Let's see. So yeah, after we accept some connection here, let's print something. Let's say tracing info, or maybe even let's just send maybe all clients, notify them that someone have connected. Like when someone have just started connecting, we're just gonna have like some info. Yeah, let's just use tracing here in this case. Honestly, tracing info, correct. And here, client. Okay, client socket ADDR connected. And by the way, you could also use client socket ADDR. Later on, we could use it like to, for example, implement banning and stuff like that. But let me know if you want, guys, if you want me to like improve on this and continue on it, but we'll see. So client have connected, great. That would just show up on the server, right? Well, honestly, I don't want to show that really. Yeah, no. You know why? Because I don't want to show the IP and the port of other people like in the stream. I mean, it doesn't matter really, but well, you gotta respect the privacy. So fine. Let's just say clients have connected, I guess. Okay, great. And then here, after we get the client name of the, after the clients have took or chose a name, what we could do here, yeah, here, before we insert the client name, we could just say, we could notify every client, for example, that the clients have connected. Let's see. So that's interesting. Let's see. Stream buff writer? No. Yes, client message sender. So send, the string is format. Actually, I'm gonna go with a format, right? And here basically the name of the client that they chose. And also I should probably gonna make sure that the client name is actually like a proper name, like an alphanumeric name, I guess. Yeah, I'm probably gonna add that too, just to make sure. And that it's, you know, that also it's the name, like let's say greater than 3 characters or something like that. But anyways, whatever. So let's say client messenger send format have connected. So yeah. And what else after that? And then we could say dot, we could give it some color. I don't know, let's say red maybe. Let's say bright red. Okay, what else? We got the socket address. For the socket address, this is basically used to identify if the message should be sent to certain clients. So here we give it the socket ADDR, I think. Yeah, so client socket ADDR. What else? And then after this, we can just turn it into a string. And use results. Great. And what's up now? Yes, here it should be client name. So client input. Oopsie, it's not here. Should do it here. Oops. Trim. And yeah, that's pretty much it, I think. Okay, next. Yeah, and one last step, I'm just gonna make sure to add some more conditions on the name. I'm gonna make sure that it's not just for max client name length, but also, like, let's say client name range, I guess. And then we could say from 0, not 0, let's say from 3 characters, let's say, to 16 characters. Expected use size but found range. Yeah, makes sense. So range, use size. Resolved, reference range. Yes. There you go. So now we have declared the client name range. Nice. Now what we could do essentially is just say client name range dot contains the length here. So basically making sure that the length of the client input, which is here the client name chosen, is inside that range. And yeah, that's it for that one. The other thing that I'm gonna make sure, here actually I'm just gonna say the name length should be in the range okay, format client name range. Okay, let's just go debug here for now. And what else? I don't know what's going on with Rust FMT, honestly. It keeps on failing. Anyways, so there you go. The name length should be in the range. Client name range. Please try again. Please try again, Asaf. Please try again. That's it. Let's go. Alright. I think that should be it. Oh yeah, I forgot about the ASCII, like, not ASCII, but alphanumeric, I guess. We could also allow spaces, just to make sure there's no weird surprises there. Like some invalid principal name or something. Anyways, let's see. So, if client input dot trim dot we could say find some char, and that char, let's say it's not, we're gonna find one that is not alphanumeric, and so basically the valid input should be alphanumeric or let's say white space. Well, the thing is I don't want all the input to be white space. Interesting. So yeah, let's remove this for now. I guess. What's up, DG? How's it going? What's up? What's up? For now, I probably am just gonna allow it's an alphanumeric just to keep things simple, probably. Later on, I could add, like, let's say, allow spaces, like white spaces, but then only, like, make sure that at least there's at least one alphanumeric value in there. And then here, let's say just this, continue. And here, let's just say the name is invalid. Only alphanumeric characters are allowed. Great. Nice. We could surely improve this. And basically, if we find some character, so basically is some, so we found some invalid character here, and then there you go. This is a char. And yeah, so if we find it, we're gonna say that it's invalid. And we're gonna basically tell, like, let the user retry. I think that should be good enough. Let's see. Oops, not this port. Right now we have this port, right? Correct. As you can see, it says that the client have connected, which is nice. And then we can tell it the name. Let's say I do some white spaces here. Ooh. What? White allowed. Interesting. Well, anyways, fine. Let's just. Ooh. Process finished with exit code 9. That's crazy. Why? That is interesting. Anyways, let's just try. And the lane length should be in range. Ooh. Yes, I see. So basically we need to be doing, so if it's none, then, well, not here actually, we're talking about this. So if not contains, then we need to tell. Great. What else? If client input is so we found an invalid character, then the name is invalid. Or like we could say char is alphanumeric. No, that wouldn't work, right? Anyways, so yeah, whatever. Let's say this now. Now C, nope. Say code taco, fine. Great. Oh, hello, I've connected. Let's go. Nice. Oh, could it be that the colors aren't there because there's no new line or something like that? Actually, correct. Like, yeah, I've probably forget about the new lines though here. That's first. And the other thing is we're saying, hello, I've connected. Let's see. Oh, what? That doesn't make good sense. What? And in fact, at least here, to have a new line. Probably here too. Probably. Looks like I missed a lot of stuff. Yeah. Let's try again. Let's see. If I say some invalid character, what, the name length? Oh yeah, well, the name length is correct. The name is invalid, only alphanumeric characters are allowed. Not sure why colors work, sometimes works, doesn't. Anyways, let's say this is coded taco. And this is some, I don't know. Yes, or yeah, fine. And there you go. I'm not sure why it does this. It's stupid. Whatever. Anyways. Hello. Ooh. How's it going? Yeah, there's an extra line there. When it comes to the message. Yeah, and the message. Okay. Where's message? Message. Come on. Message sender to string. Okay. Send the client input clone. Let's just trim the message actually. And instead of clone, let's just say toString. And I think this should do the trick. Let's give it another little test. Yeah. Go to taco. Nice. And after code attack I've connected, we don't really need a new line for some reason. Super weird. Anyways, whatever. So who can try this though? Who can test this with me now? I'm gonna send the IP. Well, first of all, of course, we're gonna I guess let's go with a no need actually. Let's just go with debug. And yes, so the server is up. Great. What else? Now we just I need to give you the IP. So this is the IP, public IP, which you're gonna use in Telnet to connect. and this is the port. Alright, these are the IP and the port that you can connect using telnet. So like you just say telnet, here you paste the IP, and here you paste the port, just like here. And hopefully you can connect. Let me know, guys, if you can connect. Let me know. I have opened the port and everything, so it should possibly work. Guess I'm gonna send the ping. All right. Let's go now. Let's just wait for someone to try to connect. Like it works for me since it's my own local network. I'd like to know if it works. It should work in theory. So it's not working. So what it's giving you? Or what it's telling you? Interesting. Maybe because I'm doing here localhost, maybe I should give it the actual IP. Okay, hold on a second, hold on. I'm gonna stop the server and maybe I'm gonna change this to my local IP, I believe. So I don't remember. How do you look up the local IP again in Linux? I think it's called IP, if I remember. Yeah, I think it's IP. Hold on. IP what? IP address? Alright. Okay, which one? Let's see. Where is my local IP? Ooh. There you go, okay. 200, okay. Alright, so maybe that was the problem, so let's try now. And yeah, right now the server is up. Can we try again? So basically telnet. Ooh, clients have connected. Okay, I think someone have connected. And I actually have hold on, I'm gonna connect first to my own thing so I could receive messages. Yeah, oops. So I think someone have connected correct. Go to Jaco. There you go, Theo have connected. Let's go. All right, so it's working over the network. Amazing. Amazing. Let's go. So we pretty much made the whole thing in live stream, and it actually works over the network. Look at that. How's it going? Of course, we have that problem of like cutting, like when there's an output, it just goes on like this. And honestly, we cannot do much about it, I think, because we need something like cross term or something like that, I guess. Or maybe there could be some sort of ASCII symbols to, like, let's say maybe delete some characters beforehand, something like that. I'd like to see how we can handle more connections. Can someone else also try to connect? So at this point, I think we have 2 connections, unless if, let's say, Theo have disconnected at that point, it probably may not even work. I should have at least, yeah, I don't handle disconnections just yet. So if someone tried and didn't work, let me know. Or I could even try myself. Okay. Yeah, it didn't tell me that Theo have connected before because I wasn't connected at that point when he connected. So there you go. So it actually works. Great. So I think mission complete to some degree. Of course, still incomplete, like we still don't handle disconnections properly. Probably don't handle some errors properly. Could probably easily, I don't know, like probably don't have limits on something. Like for example, the message is probably inbounded, like anyone could like send any big message, I guess, or something like that. But yeah, so I think we have done a good job for today. I would be interested to see. Okay, so I think I have broke since someone have disconnected. I guess they have disconnected. So let's try to launch the server once again at this point. So yeah, if anyone wants to try the server right now, I'm giving you a window to try it out. How to connect. Basically just say telnet, and the IP that I gave, the public IP. Oops. And then finally the port. Yes, just like this. And in fact, I could even, I have a domain, so I could even map my IP to my domain, and then you could just use, like, let's say the telnet domain and the port, or even just the domain, I think. Yeah, maybe. But anyways, so that's the command that you can use to connect. So if anyone wants to connect, there you go, someone have connected. And how to make it work, have connected. Hello. Though I've been testing with 2 clients, it's kind of weird when I actually write something here, it doesn't show up on the second terminal, but it actually shows up on the like a computer in another country, in the other face of the earth, something like that. Anyways, so yeah, I guess I consider this a success, maybe. Okay. How many lines of code is this? 134. Like, it's pretty parallel, like it's very efficient. So it's using multi-threading and async at the same time. Though of course it can always be improved. So yeah. Yep. Let's go. Alrighty. Okay, so it's been around 4 hours already. So if you guys want, if anyone wants to connect, it's your chance to connect now, because I gonna end the stream real soon. Yo. Okay. Though I'm not sure what is really causing the, like, when someone disconnects, it kind of breaks actually. I guess probably the way I handle, let's say, messages like errors and stuff like that. But no Chinese character support. It's probably Telnet that doesn't have Chinese character support, but like the server probably should be able to do that. It's like just sending bytes, really. It's Telnet client, I think, doesn't handle that correctly. Though later on, probably maybe next stream, we can write our own client. I'm not sure what we're gonna use to write that. Like, we could use possibly Godot or Bebe or something like that for the GUI or something. We'll see. So yeah, or we could just write it fully in Rust, maybe using cross term or something like that. But yeah, but though it should be able to, like, whatever characters, since it just sends bytes really. And even the Rust actually handles UTF-8 good. So like, for example, when I say chars here, like, I'm actually handling Unicode 8 characters correctly, so it should be working, I guess. So yeah, and I guess that's pretty much it, I guess, for the stream. That was a lot of fun. And in fact, I'm still pretty much a beginner at async, multi-threading a bit. So yeah, so that was it for this live stream, and see you later. Bye everyone. Goodbye. Okay. So, alright guys, goodbye everyone. See you later. See you maybe tomorrow. Goodbye.